The cosmological constant is now the simplest explanation for dark energy, represents the energy density of empty space. Even in a perfect vacuum, quantum mechanics predicts that virtual particles and antiparticles flicker in and out of existence. Their combined energy may not cancel out completely. This residual energy could manifest as a constant pressure pushing spacetime apart. If L is positive, as current measurements suggest, then the universe must accelerate. But there is a problem, a staggering one. Quantum field theory predicts a vacuum energy far greater than what we observe. Not 10 times greater, not 1,000,000 times, but 120 times greater, the largest known discrepancy between theory and observation in physics. This is called the cosmological constant problem. Why is the energy of empty space so small, yet not zero? Why does it begin to dominate only now, billions of years after the Big Bang? Some propose that dark energy is not a constant at all, but a dynamic force field, quintessence, that evolves over time. Others suggest modifications to general relativity on cosmic scales. A few even imagine that we live in just one bubble of a vast multiverse, and only in rare universes where L is small galaxies and life exist. But none of these theories are proven. What we know is simple and astonishing. The universe is accelerating, and dark energy is responsible. Dark energy's effects grow stronger as the universe expands. In the distant future, galaxies beyond our local group will recede faster than light can reach us, vanishing from view forever. The night sky will empty. Stars will burn out. Black holes will evaporate. In a trillion years, only cold, dim embers will remain, scattered in a universe stretched thin by endless expansion. If dark energy stays constant, this is the fate of all things, cosmic loneliness. Yet for now, dark energy does not tear galaxies or solar systems apart. Its influence is too gentle on small scales. It acts only across vast expanses of nearly empty space between galaxy clusters. Within galaxies, gravity still rules. Stars still form, planets still orbit, life still breathes. And at the heart of it all is L, the cosmological constant, a single symbol added to an equation more than a century ago, thrown away, then resurrected by the universe itself. This constant is not just a number, it is a message that space is not passive. It has energy, tension, will. It expands not because something pushes from outside, but because expansion is its nature. We stand in a universe where most of what exists is unseen and unknown. Dark matter shapes the skeleton of galaxies. Dark energy shapes the fate of the cosmos, is the quiet note underlying all cosmic symphonies, the pressure in the void that drives galaxies apart. We do not yet understand it, but we know this much. The universe is not dying with a scream or collapsing into flame. It is drifting into silence, cold, vast, accelerating outward into darkness, not with violence, but with inevitability. And in that expansion, in that U-shaped destiny, lies perhaps the strangest truth of all, that the emptiest parts of the universe hold the greatest power. They call it the energy of the vacuum. But what if dark energy is not constant at all? What if it breathes and shifts, waxing and waning over cosmic time like a hidden pulse in the universe? This is the idea of quintessence. Dark energy not as an unchanging cosmological constant, but as a dynamic field evolving, flowing, acting with purpose rather than passivity. Where L is cold and static, Quintessence is alive. It may grow, decay, or interact with matter. It may have begun stronger than it is today, or it may be gaining strength even now, and could someday tear the fabric of reality apart. In this view, dark energy is not a fixed property of space-time. It is a fluid or field, something more like the Higgs field or an ocean of scalar energy filling the universe. Unlike a cosmological constant, which has a fixed energy density and exerts constant pressure, quintessence changes as the universe evolves. It might roll slowly through a potential landscape, never settling, always adjusting to the expansion of the cosmos. Some models describe it as a light, scalar field whose energy decreases over time, others as a substance that mimics dark matter when the universe is young and dark energy when the universe ages. But why go beyond L at all? Because the cosmological constant raises as many questions as it answers. Why is vacuum energy so incredibly small? Why did it only begin to dominate cosmic expansion recently, when galaxies and life already existed? An eerie numerical coincidence known as the why now problem. Quintessence offers a possible escape from this fine-tuning. Instead of a constant energy that must be tuned to one part, in 120, quintessence naturally evolves to small values over time, like a ball rolling down a shallow hill. As it rolls, its energy density changes, allowing cosmic acceleration to begin only after billions of years. But this solution is not without cost. If quintessence exists, it must be almost unimaginably light. Its mass, perhaps 1033 electron volts, lighter than anything ever detected. It must interact so weakly with normal matter that Earth-based experiments cannot find it. It must produce a pressure-to-density ratio slightly different from 1, which astronomers measure through supernovae, galaxy clustering, and the cosmic microwave background. So far, dark energy looks very much like L, constant, unchanging. Quintessence remains unproven, a graceful idea waiting for evidence. Yet quintessence is not the only attempt to rewrite the story of cosmic acceleration. If dark energy feels unnatural, some wonder whether gravity itself is to blame. What if Einstein's theory, so successful in predicting the motion of planets and the bending of light, simply fails on the largest scales? What if galaxies do not rotate strangely because of dark matter, but because gravity weakens differently in the low acceleration environment of galactic outskirts? This is the philosophy of modified gravity. The first bold attempt came from Mordechai Milgram in the 1980s with modified Newtonian dynamics, or MON. He proposed that when accelerations fall below a tiny threshold, about 10 mass, the force of gravity does not obey Newton's inverse square law. Instead, it becomes stronger than expected, eliminating the need for dark matter to explain flat galaxy rotation curves. And he reproduced the rotation of many spiral galaxies with uncanny accuracy, using only the visible mass. No invisible halos required. But Mond struggled with galaxy clusters, which still needed unseen mass. It was also non-relativistic, not consistent with Einstein's theory, and could not explain cosmology or gravitational lensing. To address this, Jacob Bekenstein introduced TVS, tensor vector scalar gravity. This was a fully relativistic extension of MOND, able to include gravitational lensing and cosmology. Other theories followed: FIR, gravity, DGP, brain world gravity, Horndeski theories. Each tried to adjust general relativity just enough to reproduce cosmic acceleration without dark energy, or galaxy rotation without dark matter. Some proposed extra dimensions. Others introduced new fields or interactions. A few suggested that inertia itself changes in deep space. All shared the same rebellious spirit, the willingness to question gravity itself. But the universe is a harsh critic. Gravitational lensing around galaxy clusters, like the Bullet cluster, showed mass distributions separated from visible gas, consistent with invisible dark matter, not modified gravity. The cosmic microwave background revealed patterns that require dark matter to shape early fluctuations. Most crushing of all, in 2017, the binary neutron star merger GW0817 produced gravitational waves and a gamma-ray burst almost simultaneously. If gravity traveled at a different speed than light, as some modified gravity models predicted, their arrival times would have differed. They did not. Gravity and light arrived together within 2 seconds after 130 million years of travel. This killed many modified gravity models outright. Still, the question remains, is dark energy truly real, or just our way of patching a theory we do not yet fully understand? In the deep expanses between galaxy clusters, gravity may obey rules we have not fully deciphered. Some hybrid theories combine dark matter with modified gravity. Others suggest that dark matter itself might have fluid-like behavior or interact with dark energy. Perhaps quintessence and modified gravity are not rivals, but parts of a larger truth. For now, observations favor a universe with dark matter and dark energy. LCDM, the simplest model that fits reality. But simplicity in mathematics is not always truth in nature. The fact that 95% of the universe is made of unseen energy and matter should disturb us. We may only be scratching the surface of a deeper physics where spacetime, particles, and fields emerge from something even more fundamental. Quintessence imagines dark energy as a moving river, not a still pond. Modified gravity imagines spacetime itself as imperfect, bending in ways Einstein did not foresee. Both are reminders that the universe is not obligated to follow our expectations. It only follows itself. And so, the story of dark energy and gravity is unfinished. Two ideas stand opposite each other like twin silhouettes. One says space is filled with a shifting, silent field that pushes. The other says gravity lies. Between them lies a truth waiting to be discovered, hidden in the pulse of supernova, the bending of distant light, the tremors of gravitational waves, and the quiet patterns of galaxies drifting apart. They fill the universe like a whisper from creation itself. Photons that have traveled for nearly 14 billion years, stretched and cooled by the expanding cosmos until they glow faintly with the temperature of a cold winter night. This is the cosmic microwave background, the oldest light. We can see the fossil radiation left over from the Big Bang. It is not bright, not dazzling, but uniform, astonishingly uniform. Across the sky, it shines with a temperature of about 2.725 Kelvin, just above absolute zero. And yet, if you look closer, beneath that smoothness lies a map of tiny irregularities, temperature differences no larger than 1 part in 100,000. These small fluctuations, CMB anisotropies, are the seeds from which galaxies, clusters, and cosmic filaments would one day grow. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma of photons, electrons, and protons. Light could not travel freely. It scattered endlessly off electrons, bouncing through a cosmic fog. Gravity pulled matter into slightly denser regions, while radiation pushed outward. This created acoustic waves, sound waves rippling through the plasma. When the universe cooled enough for electrons to combine with protons to form neutral hydrogen, photons were suddenly released. This moment is called recombination. The fog lifted. Light broke free. And those photons have traveled ever since, redshifted by the expansion of space from visible light to microwaves. Modern satellites like COBE, WMAP, and Planck have measured this cosmic afterglow with incredible precision. They revealed the delicate mottling of hot and cold spots, regions slightly warmer or cooler than average. These patterns encode everything: the density of matter, the amount of dark matter and dark energy, the curvature of space, even the age of the universe. The peaks and troughs in the CMB's temperature-power spectrum are the frozen echoes of primordial sound waves. Their precise positions confirm that the universe is flat on large scales and composed mostly of dark matter and dark energy. The CMB is a photograph of the universe as a baby, and in those blurred features, the future is written. But the CMB does more than show temperature. It is also polarized, its light waves subtly twisted by interactions with matter. This polarization has two components: E modes, caused by density variations, and the far more elusive B modes, which could be caused by gravitational waves from inflation, the universe's earliest and most mysterious moment. Scientists search relentlessly for these B modes because detecting them would be like hearing the heartbeat of the Big Bang itself. Instruments like BICEP-3 in Antarctica and the upcoming Light Bird mission aim to capture them. After recombination, the universe entered a cosmic dark age. With no stars yet born, no light illuminated the hydrogen fog. The universe was silent, vast, and cooling. Slowly, under gravity's insistence, matter fell into the densest regions, the regions identified in the CMB. The first stars ignited a few 100 million years later, massive and brilliant, burning hot and short. Their ultraviolet light tore electrons from hydrogen atoms, reionizing the universe. This was the epoch of reionization, when darkness gave way to starlight. Reionization did not happen all at once. It began in pockets, bubbles of ionized hydrogen around the first stars, galaxies, and quasars. These bubbles grew and merged over time, carving out a Swiss cheese of ionized voids in a neutral hydrogen background. This transformation changed the behavior of light across the universe. Neutral hydrogen absorbs certain wavelengths, while ionized hydrogen does not. As stars and black holes illuminated the cosmos, the fog thinned. By around 1 billion years after the Big Bang, most of the universe was transparent again. Yet this era is one of the most difficult to observe. The early stars were often destroyed quickly, collapsing into black holes. Their light was faint and redshifted. The James Webb Space Telescope is beginning to glimpse galaxies from this time, tiny, chaotic, but unimaginably bright. Radio telescopes like LOFAR and HERA are attempting to detect the 21-centimeter signal from neutral hydrogen during the epoch of reionization. These faint whispers could show how ionized bubbles expanded, how quickly stars formed, and whether black holes contributed more to reionization than stars. Another enormous question hangs over this period. How did supermassive black holes appear so early? Quasars powered by billion solar mass black holes have been found only 700 million years after the Big Bang. How could black holes grow so large so fast? One idea is direct collapse, gas clouds that skipped star formation and fell straight into black holes. Another is that the first stars, population 3 stars, were massive and collapsed into black hole seeds. Whatever the case, these early black holes and stars flooded the universe with ionizing radiation, carving vast reionization bubbles around them. The epoch of reionization is the bridge between the smooth simplicity of the CMB and the structured complexity of galaxies. The tiny anisotropies seen in the CMB became gravitational wells. Within those wells, gas cooled, fragmented, and burst into stars. Those stars exploded as supernovae, enriching the gas with heavy elements. New stars formed from this enriched gas. Planets appeared. Somewhere, much later, life opened its eyes. Even today, the CMB and the epoch of reionization talk to each other. Photons from the CMB sometimes scatter off free electrons left over from reionization, slightly distorting the CMB's polarization. These distortions allow scientists to measure exactly when reionization happened, between 400 and 800 million years after the Big Bang. These constraints guide telescopes in their search for the first galaxies. The story of the universe is written in layers. First the Big Bang, then inflation, then the CMB, then reionization, then stars and galaxies. Each layer depends on the one before. Without the tiny temperature ripples in the CMB, there would be no seeds for gravity to grow structures. Without reionization, light would remain trapped in fog. Without dark matter halos, stars could not gather. Without dark energy, galaxies might fall back together. Every force, every field, every fluctuation participates in the long ascent from perfect symmetry to complexity. We look up at the sky and see stars, but beneath that lies a deeper vision. The afterglow of birth, mottled with the first imperfections that would become everything. And we look farther into the darkness beyond stars and see the spread of ionized light pushing back the great silence. The CMB is the first light. Reionization is the first dawn. Between them lies the most profound transformation. The universe went from a place that merely existed to a place that could begin. The universe, when viewed on the grandest possible scale, is not random. It is not an even mist of galaxies drifting in a void. Instead, it is structured, woven into a breathtaking, interconnected architecture known as the cosmic web, the largest structure ever observed. Galaxies are not isolated islands scattered without purpose. They are arranged along colossal filaments stretching hundreds of millions of light years, meeting at dense intersections called nodes, home to galaxy clusters and superclusters, while vast empty voids lie between them like cosmic oceans of near-nothingness. This is the scaffolding of the universe, shaped not by visible matter, but by the gravitational pull of dark matter acting as the unseen bones of creation. In the early universe, matter was distributed almost uniformly with only tiny fluctuations in density, 1 part in 100,000, imprinted on the cosmic microwave background. Over time, gravity amplified these small imperfections. Regions that were slightly denser than average attracted more matter, becoming denser still, while less dense regions emptied further. Dark matter, unaffected by radiation and pressure, clustered first, forming gravitational wells. Hydrogen and helium gas then fell into these invisible halos, igniting the first stars and galaxies. As time passed, small halos merged into larger ones. Streams of gas and matter flowed along the steepest gravitational slopes, and the cosmic web began to take shape. Filaments are the highways of this intergalactic landscape, immense bridges of dark matter, gas, and galaxies connecting massive clusters. Each filament can be tens to hundreds of millions of light-years long and millions of light-years thick. They are not smooth. They are speckled with galaxies like dust motes in a beam of light. Where several filaments intersect lie the nodes, galaxy clusters and superclusters containing thousands of galaxies bound together by gravity. The largest of these structures are superclusters like the Virgo supercluster and the Shapley Concentration, though even these are only small regions of a much larger web. Between the filaments are the voids, regions almost completely empty of galaxies, sometimes 100 million light-years across. Their emptiness is so vast that if the Milky Way were placed in the center of one, no other galaxy would be visible in the night sky. These voids are not dead. They are still expanding faster than their surroundings, as gravity pulls matter outwards toward filaments and clusters. In this way, the cosmic web becomes more defined with time, dense regions becoming denser, empty regions becoming emptier. Simulations such as the Millennium Simulation and Illustris have recreated this cosmic web using only 3 ingredients: dark matter, gravity, and time. They show how dark matter collapses into halos, how gas follows, how filaments stretch across space, and how galaxies form along these threads of gravity. Observations match these simulations. Redshift surveys like the Sloan Digital Sky Survey, SDSS, have mapped millions of galaxies, revealing the same filaments and voids seen in the simulations. The universe resembles sponge-like foam or a vast neural network, strings of light bound by shadows. One of the most impressive structures discovered is the Sloan Great Wall, a filamentary superstructure stretching 37 billion light-years, one of the largest known in the universe. Another is the Hercules Corona Borealis Great Wall, a mind-bending 10 billion light-years across, consisting of clustered gamma-ray bursts and galaxies, though its true nature is debated. Closer to home, our Milky Way is part of the Laniakea supercluster, Immense Heaven in Hawaiian, a gravitational region containing more than 100,000 galaxies. Galaxy clusters, nodes of the cosmic web, are the brightest beacons of structure. They are the largest gravitationally bound systems in the universe, containing thousands of galaxies, vast clouds of superheated gas emitting X-rays, and enormous halos of dark matter. The hot gas within clusters reaches temperatures of tens of millions of degrees, detectable by X-ray observatories like Chandra and XMM Newton. But even this gas pales in comparison to the mass of dark matter that holds clusters together. Without dark matter, these clusters would fly apart. The Coma cluster, the Virgo cluster, the Perseus-Pisces supercluster, all of them are jewels embedded at the intersections of filaments. The Great Attractor, lying 200 million light-years away in the direction of the Hydra and Centaurus constellations, is not a single object, but a gravitational focal point, a region where mass is concentrated enough to pull entire clusters of galaxies toward it. But beyond it lies something even more massive, the Shapley supercluster. This gigantic assembly of over 8,000 galaxies sits roughly 650 million light-years away, exerting gravitational pull across enormous distances. The Milky Way, Andromeda, and all galaxies of the local group are drifting ever so slowly toward this region, locked in a gravitational flow through the cosmic web. The formation of this web is guided by dark matter. Visible matter, gas, stars, galaxies, merely traces the outlines of something far more massive but invisible. When we map the distribution of galaxies, we are really mapping the distribution of dark matter halos. When light bends around clusters due to gravitational lensing, we are glimpsing the shape of these halos themselves. When we observe the motion of galaxies within a cluster, we feel the weight of dark matter holding them in place. In the cosmic web, everything is connected. Galaxies do not form in isolation. As gas flows along filaments, it feeds galaxies, fuels star formation, and rotates into disk shapes. When filaments funnel into clusters, galaxies collide, merge, are stripped of gas, and evolve into elliptical giants. Black holes at galactic centers grow by consuming gas delivered along filaments. Even our own galaxy is part of this system, connected to the Andromeda Galaxy by strands of dark matter and gas. At the smallest scales, dwarf galaxies trace thinner threads. At the largest scales, superclusters gather into gravitational basins surrounded by voids. Look across the night sky, and you see stars. Look deeper, through telescopes, and you see galaxies. Look deeper still, with maps of redshift and lensing, and you see the cosmic web, the true structure of the universe. Filaments, nodes, voids, all bound by dark matter, pulled by gravity, stretched by expansion, and pushed by dark energy. We live not in an empty void, but within a grand, interconnected architecture. Every galaxy, every cluster, every atom in our bodies lies somewhere in this vast network. The cosmic web stretches from one edge of the observable universe to the other, a frozen trace of gravity sculpting time itself. It is the fingerprint of creation and the pathway of destiny, a bridge between the Big Bang and the accelerating future. And while stars burn and die, galaxies collide, and black holes devour, the web endures, silent, invisible, eternal. They stretch like tendrils of a colossal, invisible organism, vast bridges of galaxies, dark matter, and primordial gas connecting distant corners of the cosmos. These are galaxy filaments, the largest known structures in the universe, cosmic highways upon which galaxies travel, merge, and evolve. Unlike clusters, which are dense knots of galactic matter, or voids, which are cosmic deserts, filaments form the ribs and sinews of the universe's great architecture. They are the connective tissue of creation, the framework upon which all structure is built. Each filament spans tens to hundreds of millions of light years, and some stretch for over 1 billion, threading through the darkness and converging like rivers into gravitational oceans, the galaxy clusters and superclusters that anchor them. In the earliest epochs of the universe, matter was almost evenly spread, aside from minuscule ripples in density. These ripples, recorded in the cosmic microwave background, became amplified through gravity. Dark matter pulled into slightly denser regions, forming elongated troughs and strands. Over billions of years, these strands evolved into filaments. Ordinary matter followed, cooling into clouds of hydrogen that condensed to form stars and galaxies. As small galaxies grew along the filaments, gravity pulled them toward intersections, nodes where they collided and merged to form larger galaxies and clusters. The filaments themselves remained largely invisible, made mostly of dark matter and faint, diffuse gas that rarely emits light. Only in recent decades have we begun to truly observe these filaments directly. Large galaxy surveys, like the Sloan Digital Sky Survey (SDSS), revealed that galaxies are not randomly distributed but arranged along vast arcs and bridges. When their positions were plotted in 3 dimensions, they revealed a cosmic web, galaxies forming strings and walls surrounding enormous spherical voids. Some filaments, such as the Sloan Great Wall, span more than 1 billion light-years. Others are smaller and feed clusters like the Virgo or Coma clusters, funneling galaxies and gas like conveyor belts of gravity. These filaments are not just beautiful, they are dynamic. Galaxies inside them move along their lengths, slowly migrating toward denser intersections. Gas flows along these same channels, feeding star formation in galaxies that lie within. In some galaxies, especially in the early universe, cold streams of hydrogen from filaments helped build massive spiral disks. Some astronomers call this cosmic plumbing, dark matter and gravity carving pipes through which the raw material of stars flows. The Milky Way itself sits in a filament, linked not only to Andromeda and the local group of galaxies, but also Tauri currents of mass flowing toward a distant gravitational hub. That hub has a name: Laniakea. The Laniakea supercluster is our cosmic address, the magnificent basin of gravity to which our galaxy belongs. Its name means immense heaven in Hawaiian, a tribute to both the Pacific navigators who first explored Earth's oceans and the cosmic navigators who now map the seas of galaxies. Laniakea is not just a cluster of galaxies, but a vast gravitational domain, a continent in the cosmic web. It spans over 520 million light-years and contains around 100,000 galaxies. At its heart sits the Great Attractor, a mysterious region that pulls galaxies toward it, not through light, but through gravity alone. Our Milky Way lies on the edge of this colossal structure, part of a smaller group known as the Local Group, which includes Andromeda and dozens of dwarf galaxies. The Local Group, in turn, sits on the outskirts of the Virgo cluster, a collection of over 1,300 galaxies located about 55 million light-years away. The Virgo cluster itself is only a small node within the flowing landscape of Laniakea. Like water in a basin, galaxies within Laniakea flow toward the same gravitational valleys, toward Virgo, toward Hydra Centaurus, toward the Great Attractor. These motions are slow on human timescales, millions of years for small shifts, but clear across cosmological distances. This flow is what defines Laniakea, not merely as a group of galaxies, but as a region of coherent motion, a grand gravitational watershed. Laniakea is bounded by gravitational divides, regions where galaxy motions diverge, flowing toward other superclusters like Perseus Pisces or Shapley. Beyond it lies the Shapley supercluster, one of the most massive concentrations of galaxies in the local universe, lying over 650 million light-years away. Its enormous gravity tugs even on Laniakea itself, like a deeper valley attracting water across mountain ridges. This interplay between gravitational basins explains why our galaxy and its neighbors are not only rotating around the local group's center of mass, but also drifting at nearly 600 kilometers per second toward the Great Attractor and beyond. Filaments serve as the roads that lead toward these nodes. The Milky Way is connected via slender dark matter bridges to the Virgo cluster, and ultimately to Laniakea's core. These bridges are not always filled with bright galaxies. Some are traced by faint dwarf galaxies, others remain nearly dark, glowing only in ultraviolet or X-ray from sparse hydrogen heated by collisions or cosmic rays. Recently, astronomers used powerful observatories like the Chandra X-ray Observatory and the Atacama Large Millimeter-Submillimeter Array ALMA to peer into these filaments and detect the warm, hot intergalactic medium, WIM, a tenuous gas at a few 100,000 to a few million degrees Kelvin. This WIM may contain much of the universe's missing baryonic matter, not seen in stars or galaxies, but hidden in the vast connective threads of the cosmic web. Even black holes are not exempt from this architecture. Supermassive black holes at the centers of galaxies may grow more quickly if their host galaxy lies along a filament. Feeding off a steady stream of infalling gas, they power quasars that shine brighter than entire galaxies, lighting up the filaments like beacons in the night. Some quasars observed at high redshift, less than 1 billion years after the Big Bang, lie at intersections of primordial filaments where gas was abundant and gravity fierce. Filaments also influence galaxy evolution. Galaxies within them often show higher star formation rates than isolated galaxies in voids. Those closer to nodes, where filaments meet clusters, can be stripped of their gas by interactions, becoming quiescent galaxies. This journey from filament to cluster is sometimes called cosmic urbanization, galaxies migrating from rural filaments to the crowded city centers of clusters where they lose gas, collide, and age. To map this vast structure is to see the universe not as a random scatter of stars, but as a living, breathing organism. The cosmic web grows over time, stretching under dark energy, strengthening under dark matter, evolving as galaxies drift along its filaments like leaves on invisible rivers. The Laniakea supercluster is our home within this web, a colossal archipelago of galaxies bound not by light, but by the most ancient force of all, gravity. When we look up at the night sky, we see stars. When we look deeper, we see galaxies. But when we look deeper still, beyond light, beyond the visible, we see filaments, nodes, voids, and currents, universe that is not chaos, but structure, not empty, but interconnected. We see the path the Milky Way travels, the river of gravity leading us slowly toward the Great Attractor across the basins of Laniakea. We are not alone, not static, not isolated. We are part of a structure so large it takes light 500 million years to cross, yet so delicate it was born from quantum fluctuations in the first instant of existence. The cosmic web and Laniakea remind us that the universe is not only vast, it is connected, and somewhere along one of its filaments, on the edge of a modest galaxy, on a small blue planet, we have begun to map the threads of our cosmic home. They call it the unseen hand of the cosmos, a vast, invisible pull drawing galaxies, clusters, and entire sections of the local universe toward a mysterious region in space. This phenomenon is known as the Great Attractor, a gravitational anomaly so powerful that even the Milky Way, Andromeda, and thousands of neighboring galaxies are drifting toward it at hundreds of kilometers per second. And yet, for decades, astronomers could barely see it. The reason is simple. It lies hidden behind the dense plane of our own galaxy, shrouded by dust, gas, and stars. We live inside a cosmic river of motion, drawn like iron to a magnet, but the source of that pull is cloaked like a mountain behind clouds. The story begins with peculiar velocities, the motion of galaxies that cannot be explained by cosmic expansion alone. In theory, if the universe were perfectly uniform, galaxies would recede from each other in all directions according to Hubble's law. The farther away, the faster they move. But when astronomers in the 1970s measured galaxy motions relative to the cosmic microwave background, they found something strange. The Milky Way, instead of resting softly on the expanding fabric of space, was racing through it at more than 600 kilometers per second in a specific direction, toward the constellation Centaurus. And not just our galaxy. The entire local group was moving in that direction. Something massive lay ahead, pulling us in. They named it the Great Attractor, not a galaxy, not a black hole, but an overdensity of mass on an enormous scale. Over time, deeper sky surveys, X-ray maps, and infrared telescopes were used to pierce the dust of the Milky Way's zone of avoidance, revealing a dense region of space around 150–200 million light-years away near the Norma cluster, Abell 3627. The region teems with galaxies forming a dense cluster complex. The Great Attractor is estimated to contain hundreds of trillions of solar masses. Yet even this might not be the ultimate source of our motion, because beyond it lies something even more colossal. Deeper still, at around 650 million light-years away, sits the Shapley supercluster, also known as the Shapley Concentration, one of the most massive structures in the nearby universe. If the Great Attractor is a hill of gravity, then Shapley is a mountain. It contains more than 24 rich galaxy clusters, anchored by the enormous cluster Abell 3558. The mass of the Shapley concentration is estimated at over 10,016 solar masses, enough to dominate the gravitational flow of galaxies across a staggering volume of space. While the Great Attractor was once thought to be the endpoint of our motion, we now know that it is only a waypoint, a step along a larger river of matter flowing into Shapley. These gravitational flows are not like orbital motions. They are not circular or bound. Instead, galaxies drift slowly along the filaments of the cosmic web toward the deepest gravitational wells. Think of it as water in an immense basin. Everything within our Laniakea supercluster, our home supercluster, stretching over 520 million light-years, is flowing inward, not to the Milky Way, not to Virgo, but toward the Great Attractor. And beyond that, toward Shapley. Our motion through space is not random. It is choreography written by gravity. The Shapley supercluster was first identified in the 1930s by astronomer Harlow Shapley, who noticed an unusually high concentration of galaxies in the region of the constellations Centaurus and Hydra. But its true nature was not fully understood until the late 20th and early 21st centuries, when modern redshift surveys and X-ray observations revealed the scale of its mass. It is a colossal assembly of galaxies, clusters, and dark matter, an entire continent of cosmic structure. Powerful telescopes show arcs, filaments, and webs of galaxies stretching into Shapley like veins converging on a heart. What makes both the Great Attractor and Shapley especially fascinating is that they cannot be understood by light alone. The majority of their mass is dark matter, unknown, invisible, detectable only by its gravitational pull. We map their presence not by what they emit, but by how they distort space. Galaxies between us and Shapley show gravitational lensing. Light from even more distant galaxies is bent, magnified, or smeared by the mass of intervening clusters. Hot, X-ray emitting gas fills the cluster cores, heated to tens of millions of degrees by colliding galaxies and dark matter halos. Even so, there are still mysteries. Some galaxies move faster or in slightly different directions than models predict, suggesting there may be other mass concentrations, perhaps in the Vela supercluster or the dipole repeller, a region of unusually low density that pushes galaxies away like a gravitational void. This reveals a deeper truth. Motion in the universe is not caused only by where mass is located, but also by where mass is absent. Galaxies fall into wells and are pushed from hills of emptiness. In time, the Great Attractor and even Shapley will fade from our view. Dark energy, which accelerates cosmic expansion, will eventually dominate gravity. Galaxies not gravitationally bound to the local group will drift away faster than light can reach us. But for now, we are still part of the Great Infall. Our galaxy, our local group, our Virgo cluster, all are falling toward the gravitational center of Laniakea, drawn onward toward the Great Attractor, and beyond that, toward the Shapley supercluster. If one could step outside the Milky Way and watch in time-lapse over billions of years, one would see an elegant flow of galaxies, like sparks pulled into a whirlpool. The cosmic web bends and warps as matter cascades toward Shapley, the densest knot in our section of the universe. The Great Attractor acts as a slope, pulling us downward, and Shapley is the cavernous valley into which we all flow. Humanity has existed for barely a heartbeat of cosmic time, and yet we have already mapped these gravitational pathways, traced them through redshift surveys, X-ray emissions, and microwave background measurements. We know our motion through the universe is not random. We are part of an immense migration, an unending drift along the threads of dark matter. The Great Attractor and the Shapley Concentration are signposts in this journey, ancient gravitational beacons, calling not with light, but with silent force. Someday, galaxies will no longer be visible to each other. The night sky will be locked within the local group, as dark energy pulls everything else beyond the horizon. But even then, buried in the background radiation and in the motions of ancient stars, there will remain a record of this journey, of the Great Attractor that tugged us forward, and of the Shapley supercluster that anchored our path. We are not stationary. We are not isolated. We are falling, slowly, silently, through the curvature of space-time, along the filaments of the cosmic web, into the heart of gravity itself. They are the silent chambers of the universe, vast regions where there are almost no galaxies, no clusters, no light. These are galaxy voids, immense stretches of nearly empty space, the dark gaps between the filaments of the cosmic web. If galaxy clusters are the bright cities of the cosmos, voids are the dark countryside, quiet, lonely, and staggeringly large. The Boötes Void is perhaps the most haunting of them all. Discovered in 1981 by Robert Kirshner and his team, it lies in the direction of the constellation Boötes, a nearly spherical gulf, 330 million light-years across. Inside it, instead of thousands of galaxies as one might expect in such a volume, there are barely a few dozen. The cosmos there is thin, quiet, and starved of matter, a near absence rather than a structure. Voids like this are not rare. They make up nearly 80% of the observable universe by volume, though only a tiny fraction of its mass. They are the flip side of galaxy clusters. Where gravity pulls matter inward to make superclusters, it also drains matter away from other regions, leaving behind bubbles of emptiness. These voids are outlined by the same cosmic web that holds galaxies. Filaments and sheets of galaxies form their walls, while the interiors remain sparse. The Boötes Void is so large that if the Milky Way sat at its center, we would not have discovered other galaxies until the 1960s. It is not a hole carved out of space, but a place that never filled, like a balloon of near-nothingness expanding within everything. The formation of voids traces back to the primordial fluctuations in the early universe. Slightly underdense regions, areas where matter was a bit less concentrated, expanded faster than the rest of the universe due to lower gravitational pull. As time passed, they drained further, becoming emptier while matter accumulated elsewhere. Over billions of years, these voids stretched, merged, and inflated like bubbles in a rising loaf of bread. Small voids collided to form larger supervoids, irregular, almost spherical regions spanning hundreds of millions of light years. The Boötes Void is likely one such supervoid, a fusion of several smaller voids. Voids are not perfectly empty. They still contain dark matter, thin tendrils of gas, and the occasional lonely galaxy, isolated, starved of intergalactic material, evolving slowly and undisturbed. These void galaxies are often small, blue, and rich in gas. With no neighboring galaxies to disrupt them, they form stars at a leisurely pace, unhurried by collisions or tidal forces. Some are thought to be among the most pristine galaxies in the universe, relics of an earlier era when galaxies were untouched by mergers. Galaxy voids also affect the cosmic microwave background. Light traveling through a supervoid like Boötes may lose a slight amount of energy due to the integrated Sachs-Wolf effect, where dark energy subtly alters the gravitational landscape over time. Behind a void, the CMB becomes microscopically colder, a faint fingerprint of emptiness etched onto the oldest light in existence. In this way, even nothingness leaves a mark on the universe. If voids are the silent spaces between cosmic structures, the Sunyaev-Zeldovich SZ effect is one of the most remarkable ways the universe reveals its crowded places, galaxy clusters, by how they distort ancient light. First described by Rashid Sunyaev and Yakov Zeldovich in the 1970s, this effect occurs when photons from the CMB pass through a galaxy cluster and interact with hot electrons in its intracluster gas. The gas inside galaxy clusters is extremely hot, tens of millions of degrees Kelvin, heated by gravity and collisions. When CMB photons cross these plasma oceans, they gain a small amount of energy by scattering off the fast-moving electrons. Their wavelengths shift slightly from microwave to higher energy frequencies. The effect is tiny, but measurable, a fingerprint of invisible cluster gas stamped onto the background of the universe. What makes the SRZ effect extraordinary is that it does not fade with distance. Light from distant clusters gets dimmer as they recede, but the SZ distortion remains just as strong. That means astronomers can detect galaxy clusters billions of light years away, clusters that would otherwise be impossible to see with optical telescopes. The SZ effect thus acts as a spotlight for the unseen universe, revealing clusters hidden behind dust, beyond redshift, or in regions with little visible light. There are two primary types of SZ effect. The thermal SZ effect is caused by the random thermal motion of electrons in the hot cluster gas, which boosts the energy of passing CMB photons. This produces a distinctive spectral distortion, a dip in CMB intensity at low frequencies and a rise at high frequencies. The kinetic SZ effect, much weaker, occurs when a cluster as a whole moves toward or away from us. In this case, CMB photons gain or lose energy due to the bulk motion of the hot plasma. Studying both allows astronomers to measure the temperature of cluster gas, the cluster's velocity through space, and even infer how dark matter influences its motion. The SZ effect also allows us to count galaxy clusters across cosmic time. Surveys like the South Pole Telescope, SPT, Atacama Cosmology Telescope, ACT, and Planck Satellite have mapped thousands of SZ clusters, constructing catalogs that stretch deep into the early universe. The distribution and abundance of clusters tells us how structure grew and how dark energy accelerated cosmic expansion. By comparing SZ data with X-ray maps, astronomers can determine the ratio of gas to dark matter, test models of gravity, and even search for deviations from Einstein's theory. When combined with gravitational lensing, the SZ effect becomes a tool for mapping both visible and invisible matter. Light from distant galaxies bends around massive clusters, tracing dark matter halos. Meanwhile, the SZ effect reveals the hot gas trapped in their gravitational grip. Together, they offer a full picture of a cluster's anatomy: dark matter bones, gaseous flesh, and stars glowing like sparks on the surface. So the universe speaks in two voices, one of emptiness, one of collision. Voids are the quiet between the notes, great regions of cosmic silence. The SZ effect is the vibration of those same cosmic strings when galaxies gather, collapse, and ignite in heat. One shows us the absence of matter. The other shows us matter under pressure. One stretches hundreds of millions of light years in cold nothingness. The other grows around galaxy clusters where ancient radiation is twisted by hot electrons. Together, they reveal that the universe is neither full nor empty, neither chaotic nor ordered, but a balance between structure and void, between light and silence. And in that balance, we find our place. They are silent distortions written across the universe, invisible to the naked eye, yet imprinted into every distant galaxy we see. Light, which travels in straight lines through empty space, bends and warps as it passes through the cosmic landscape, sculpted by gravity. This is gravitational lensing, Einstein's great insight that mass curves, space, and light must follow that curvature. In most cases, the bending is subtle, barely noticeable. But when measured carefully across millions of galaxies, these distortions reveal the unseen structure of the universe itself. This faint distortion is known as cosmic shear, the result of weak gravitational lensing, and it is one of the most powerful tools humanity has to map dark matter and trace the scaffolding of the cosmic web. Cosmic shear does not produce dramatic arcs or rings in the sky. Instead, it gently stretches or compresses the shapes of background galaxies as their light passes by galaxies, clusters, filaments, and dark matter halos. The effect is so small that it can only be detected statistically by analyzing the shapes and orientations of millions of galaxies. Each galaxy is naturally elliptical or irregular, but if a slight alignment appears across the sky, stretching many degrees across, it signals that their light has been distorted by large-scale gravitational fields. To detect these minuscule distortions, astronomers use wide-field sky surveys such as the Canada-France-Hawaii Telescope Lensing Survey, the Dark Energy Survey, the Kilo Degree Survey, and soon the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST. These projects observe hundreds of millions to billions of galaxies, measuring how their shapes deviate from random alignment. The patterns of Shear allow researchers to construct maps of dark matter distribution, ghostly, transparent landscapes showing where matter lies, even when no stars or galaxies are present. Cosmic shear provides direct evidence for dark matter and its role in shaping the universe. Unlike galaxies, which can move and interact, dark matter responds only to gravity. As a result, dark matter structures form first, creating a framework into which galaxies later fall. Weak lensing maps show how dark matter filaments connect galaxy clusters across enormous distances and how voids remain empty and smooth. These observations match the predictions of cosmological simulations superbly, reinforcing the cold dark matter model as a cornerstone of modern cosmology. Yet cosmic shear does more than map dark matter. It also measures the influence of dark energy. As the universe expands, structures grow under gravity. But dark energy counteracts this growth by accelerating expansion, stretching space, and slowing the collapse of matter into clusters and filaments. Cosmic shear tracks this growth over time by observing galaxies at different distances and therefore different epochs in cosmic history. If dark energy changes with time, or if gravity behaves differently on cosmic scales than Einstein predicted, cosmic shear will reveal these deviations. If weak lensing is the universe whispering its secrets, strong gravitational lensing is when it speaks clearly and dramatically. When a massive object, like a galaxy cluster or a particularly dense galaxy, lies directly between Earth and a distant galaxy or quasar, it can bend light so intensely that it creates multiple images, arcs, or even complete circles of light. These perfect circles are called Einstein rings, named after the man who first predicted their existence in 1936. They occur when the observer, lens, and background source are precisely aligned. In these moments, the universe becomes a vast, natural telescope. Einstein rings are breathtaking. A single galaxy may appear as a glowing circle surrounding a darker foreground galaxy, like a cosmic halo. Sometimes the alignment is not perfect, and instead of a complete ring, we see arcs, stretched and curved smears of light wrapping around the lensing object. In the most dramatic cluster lenses, entire galaxies are pulled into delicate arcs and streamers, as in the famous Hubble 370, the Horseshoe Einstein ring, or the mesmerizing Einstein cross, where a single quasar is split into 4 distinct points around a central galaxy. Strong lensing allows astronomers to measure the mass of the lensing object with astonishing precision, including its dark matter content. The positions and shapes of the lensed images depend only on gravity, not on the light emitted by stars or gas. As a result, lensing reveals dark halos, invisible spheres of dark matter surrounding galaxies and clusters. In clusters like the Bullet cluster, strong lensing shows that most of the mass lies in dark matter, separate from the hot gas seen in X-rays, one of the strongest proofs that dark matter is real and distinct from normal matter. Einstein rings also act as powerful magnifying glasses. Because the light of distant galaxies is bent and focused, objects behind the lens appear brighter and larger than they would otherwise. This has allowed astronomers to observe galaxies from the early universe that would be too faint to detect directly. Some of the most distant known galaxies, seen when the universe was less than 1 billion years old, were discovered thanks to strong gravitational lensing by foreground clusters. Time adds another layer of brilliance to these cosmic lenses. Light, traveling around opposite sides of a lensing galaxy, takes different paths and therefore arrives at slightly different times. If the lensed object is a quasar, whose brightness flickers over days or weeks, astronomers can measure time delays between each image of the quasar. From these time delays, they can calculate the expansion rate of the universe, an independent measurement of the Hubble constant. This method has revealed a tension. Lensing-derived values of the Hubble constant are higher than those inferred from the cosmic microwave background, hinting that something in our cosmological model may be incomplete. Together, cosmic shear and Einstein rings reveal the universe not only in light, but in distortion. Space itself behaving like glass, bending and stretching the images of galaxies across billions of light years. Weak lensing uncovers the invisible skeleton of dark matter that gives the cosmos its structure, while strong lensing transforms clusters into natural telescopes, magnifying the distant past. We live in a universe where space is not flat and empty, but curved and sculpted by gravity. Light is not just illumination, but a messenger, carrying with it the warps and curves of space-time. And by studying the way galaxies are subtly stretched or dramatically ringed, we are not just looking at distant objects, we are tracing the invisible hand of gravity itself. Light from distant galaxies and quasars does not always follow a single, straightforward path to our eyes. Sometimes, gravity bends it, splits it, delays it, and shapes it into patterns across the sky. Among these phenomena, strong gravitational lensing time delay systems stand as some of the most remarkable tools in modern cosmology. In these systems, a distant quasar or galaxy lies behind a massive foreground object, usually a galaxy or galaxy cluster, that warps space-time so intensely that it creates multiple images of the same source. Yet because each image is formed along a path of different length and gravitational depth, the light does not reach Earth at the same moment. Instead, it arrives staggered in time, sometimes by hours, sometimes by weeks, sometimes by months. This difference is the time delay, a direct imprint of cosmic geometry and expansion on the canvas of the universe. Imagine a quasar billions of light years away, its light bending around a massive galaxy sitting directly in front of it. The lensing creates multiple images, perhaps 4 points around the lens like a cross, or 2 elongated arcs. The quasar flickers unpredictably over time, its brightness rising and falling as gas spirals into its central black hole. Each lens image shows the same pattern of brightness changes, but shifted in time. By measuring those time shifts precisely, astronomers can calculate the difference in path length and gravitational potential for each route the light took. Combined with the redshift of the objects and models of the lensing mass, this allows an extraordinary achievement, measuring the Hubble constant, the rate at which the universe expands. These time delay lens systems, such as the famous Einstein cross, Q223700305, RxJ10311131, or the quasar HE04351223, are not only beautiful but crucial in addressing a fundamental tension in cosmology. Measurements of the Hubble constant using the cosmic microwave background suggest one value, while measurements from supernovae in the local universe suggest another. Time delay lenses provide a completely independent method. In recent years, projects like DuraLICUW, H-SPO lenses in Cosmos Grail's wellspring have used these systems to calculate the Hubble constant with percent-level precision. Their values often align more closely with the local measurements than with those from the CMB, suggesting that either unknown physics lurks in the early universe or that our models need revision. In this way, delayed light from the distant universe becomes a messenger of cosmic truth, whispering that something in our understanding might be incomplete. The reason this method works is that gravity and space-time are intertwined. Light traveling close to a massive object experiences a delay not only because its path is curved, but also because time itself flows slower near mass. This gravitational time dilation is predicted by general relativity and has now been confirmed across billions of light years. Each time delay lens is a cosmic laboratory where we can watch gravity alter time. While light bends around galaxies to reveal the universe's grand structure, another process plays out on a much smaller scale, within dusty disks of gas surrounding newborn stars. These are protoplanetary disks, the birthplaces of planets. Once thought to be simple, featureless disks of dust and gas, they are now known to be structured with astonishing precision. Rings, gaps, spirals, vortices, and arcs sculpt the material around young stars like the grooves on an ancient record. And it was the Atacama Large Millimeter Submillimeter Array, ALMA, that revealed this beauty to us. Perched atop the Chilean desert at 5,000 meters above sea level, ALMA observes the universe in millimeter and submillimeter wavelengths, perfect for detecting the cold dust in protoplanetary disks. In 2014, ALMA produced one of the most iconic images in astronomy. The disk around the young star, HL Tauri, located about 450 light-years away. The image showed a series of bright and dark concentric rings, gaps where material appeared to be missing, likely carved by forming planets still embedded in the disk. Stars only 1 million years old, cosmically newborn, were already building planets. This one image overturned long-held assumptions, showing that planet formation begins much earlier than once thought. Since HL Tauri, ALMA has observed dozens of protoplanetary disks in exquisite detail. Some, like those around TW Hydrae, AS209 or PDS70, show vast gaps, hundreds of millions of kilometers wide, dust-free zones that align with planetary orbits. In PDS70, ALMA and the Very Large Telescope even imaged 2 forming planets directly, still glowing in infrared as they accrete matter. Spirals twist outward in some disks, possibly driven by gravitational instabilities or by giant planets perturbing the gas. In others, asymmetric dust traps form crescents, vortices where pebbles gather, perhaps the first step toward building planetesimals and eventually terrestrial worlds. These substructures, rings, gaps, spirals, appear not only around sun-like stars, but also around red dwarfs and massive stars. The physics behind them involves a complex interplay of gravity, pressure, turbulence, magnetic fields, and radiation. Dust grains collide and stick together, forming pebbles and boulders. Gas flows inward due to viscosity, but planets disrupt this flow, opening gaps and creating pressure barriers where dust collects. Some rings may form not from planets, but from ice lines, the distances at which different molecules freeze onto dust grains, changing their stickiness and dynamics. Carbon monoxide freezes further out than water, creating distinct chemical rings. In this way, chemistry leaves physical imprints on the architecture of the disk. What makes ALMA's revelations so powerful is their resolution. Observing at wavelengths of 1 millimeter with baselines up to 16 kilometers, ALMA can detect structures the size of Earth's orbit in systems hundreds of light-years away. Each disk becomes a map of planetary footprints, worlds still cloaked in dust, unseen but unavoidable in their gravitational effects. The diversity of these disks hints at the diversity of planets, some destined to form compact solar systems, others stretched into wide orbits with gas giants and frozen debris. From the bending of ancient quasar light to the sculpting of dust around infant stars, gravity weaves the universe at every scale. In strong lensing time delay systems, we witness gravity slowing time and splitting light to measure the expansion of the cosmos. In protoplanetary disks, we see gravity gather dust into rings and carve gaps where new worlds ignite. One reveals the geometry of the universe. The other reveals how small worlds like Earth begin. This is the beauty of astronomy. It connects the vast and the tiny, the oldest light in existence with the faintest dust around a young star. And through tools like gravitational lensing and ALMA's millimeter eyes, we glimpse not just where the universe has been, but where it is going, and where planets like ours come from. They are whispers in the atmospheres of distant worlds, faint chemical traces carried on starlight, subtle signatures that may one day answer the greatest question humanity has ever asked: are we alone? Atmospheric biosignatures are molecules, combinations of gases or chemical imbalances that, on Earth at least, are strongly associated with life. When a planet passes in front of its star, a small fraction of starlight filters through its atmosphere, imprinting the spectral fingerprints of gases like oxygen, methane, ozone, or even dimethyl sulfide, a compound released by plankton in Earth's oceans. Detecting these signatures over interstellar distances is one of the most delicate and ambitious scientific efforts of our time. Yet telescopes like the James Webb Space Telescope, JWST, and future missions like LUVOIR and HABEX are beginning to peer into alien skies, searching for hints of biology among the stars. Life alters planetary atmospheres. On Earth, photosynthetic organisms flood the air with oxygen, which otherwise would react away quickly with minerals or volcanic gases. Methane is produced by microbes and decays within decades when oxygen is present, so their coexistence, in large amounts, implies constant renewal, something geology alone struggles to provide. This disequilibrium has become one of the strongest theoretical biosignatures. A planet with both oxygen and methane might be breathing. But the universe offers trickery. Ultraviolet light can split water molecules on hot, barren planets, allowing hydrogen to escape to space and leaving behind oxygen without any life involved. Methane can erupt from volcanism. Even ozone, a byproduct of oxygen, might form abiotically. So biosignatures are not proof on their own. They are evidence that must be weighed against models of geology, stellar radiation, and atmospheric chemistry. Scientists now speak of biosignature frameworks, layering context upon detection. To claim life, one must detect multiple molecules simultaneously and understand the planet's environment. For example, a planet with abundant oxygen, little carbon monoxide, surface water vapor, and a temperate climate becomes a strong candidate. Methane alongside carbon dioxide, without signs of volcanic gases like sulfur dioxide, strengthens the case further. Compounds like nitrous oxide from bacteria, methyl chloride from ocean life, or phosphine, recently controversially reported in Venus's atmosphere, are also considered. These are secondary biosignatures, less common but potentially powerful when combined with others. Future telescopes aim to extend our reach. STIL-WST can detect carbon dioxide, methane, water vapor, and possibly oxygen in transiting exoplanets. The Extremely Large Telescope, ELT, on Earth will directly image rocky planets around nearby stars, resolving spectral signatures from their atmospheres. Further still, proposed space telescopes like LUVOIR or HABEX will block out the glare of stars using star shades or coronagraphs, capturing the faint reflected light of Earth-sized planets. From that light, scientists hope to see red edge, the wavelength where vegetation on Earth reflects strongly, or seasonal variations in atmospheric gases, or even glints of light from oceans. But biosignatures are only half the story. A living world is not just a planet, it is a system. It likely has weather, oceans, continents, and a moon. And that brings us to one of the most tantalizing subjects in modern astronomy: exomoons. Just as planets orbit stars, moons orbit planets, and some of these moons, like Europa or Enceladus, may even be habitable while their planets are not. So if planets can host life-bearing moons, then the search for life must expand beyond exoplanets to exomoons, still unseen but increasingly within reach of detection. Exomoons are extraordinarily difficult to find. They do not emit their own light, and they are even smaller than the planets they orbit. But their presence can be inferred indirectly. When a planet transits a star, the timing of its transit and its duration can be slightly altered by the gravitational pull of a moon. The transit timing variations, TTV, and transit duration variations, TDV, method. In rare cases, a moon might also transit the star slightly before or after the planet, creating an additional, small dip in brightness. Another method is through the wobble of a planet's velocity as the moon tugs on it. All these effects are tiny, but with precise observations from Kepler and now JWST, astronomers have identified several intriguing candidates. The most famous is Kepler Shunt 1625 I, a potential Neptune-sized moon orbiting a Jupiter-sized planet located about 8,000 light-years away. Observations from Kepler suggested unusual timing and depth variations in the planet's transits. Follow-up data from the Hubble Space Telescope added weight to the possibility of a large moon. If confirmed, it would be a Titan, far larger than any moon in our solar system, perhaps more like a binary planet system than a typical planet-moon pair. Another candidate, Kepler 1708bi, has also been proposed, yet both remain unconfirmed, partly because confirming an exomoon often requires catching multiple transits with no ambiguity, and such opportunities are rare and fleeting. Despite the scarcity of confirmed detections, theory suggests exomoons should be common. Gas giants form early in planetary systems, and as they grow, they are surrounded by circumplanetary disks, miniature versions of protoplanetary disks, from which moons can accrete. Simulations indicate that moons around such planets may be Earth-sized. If these planets orbit within their star's habitable zone, their moons may be warm enough for liquid water. Even outside habitable zones, tidal heating, like that which warms Jupiter's Europa or Saturn's Enceladus, could sustain subsurface oceans beneath icy crusts. In such places, life could emerge without sunlight, powered instead by chemical energy and internal heat. In the decades ahead, detecting the first confirmed exomoon will be a watershed moment. But even more profound will be studying their atmospheres. A moon orbiting a giant planet may pass through the planet's magnetosphere, shielded from radiation, or experience auroras and volcanic heating. Its atmosphere might be thin, like Mars's or thick like titans. If biosignature gases were detected in such a moon's atmosphere, methane, oxygen, water vapor, it would challenge the Earth-centric view that life is found only on planets. It would suggest that life clings to gravitational pockets wherever energy and water can combine. Atmospheric biosignatures and exomoons both belong to the frontier where science edges into discovery. One seeks signs of alien life in chemical whispers. The other searches for worlds hidden in the gravitational embrace of larger ones. Together, they extend our imagination from mere exoplanets to living systems, planets, moons, atmospheres, oceans, magnetospheres, all intertwined. Perhaps somewhere, not too far from here, a moon orbits a blue world, clouds drifting across its skies. In its atmosphere, molecules are out of balance, not by accident, but by biology. And above that moon's horizon, its planet hangs enormous and luminous, a reminder that in this universe, life may grow in the places we least expect. They wander through the darkness, unbound by the warmth of any star, cold and silent travelers adrift in interstellar space. These are rogue planets, free-floating worlds cast out from their home systems or born in solitude between the stars. They drift through the galaxy unseen, except when their gravity briefly bends starlight or betrays their presence in the infrared glow of residual heat. They do not orbit suns. They do not witness dawn or dusk. They are cosmic orphans, and yet within their cold interiors, some may harbor subterranean oceans, internal heat, and even the conditions necessary for life. The existence of rogue planets was once the realm of science fiction. But gravitational micro-lensing surveys such as OGLE, Optical Gravitational Lensing Experiment, and MOA, micro-lensing observations in astrophysics, have revealed their subtle footprints. When one of these dark planets passes in front of a distant star, its gravity briefly magnifies the star's light, producing a flicker, a signature lasting hours or days, depending on the planet's mass. Some micro-lensing events show no accompanying star at all, only the gravitational tug of a planet-sized mass drifting alone. There could be billions of them in our galaxy, perhaps as many as there are stars. Some estimates suggest that for every main sequence star, there may be one or more rogue planets wandering through the void. How do such worlds form? There are two leading theories. The first is violent exile. In young planetary systems, gravitational chaos reigns. Gas giants migrate inward and outward. Rocky planets collide, and unstable configurations fling smaller bodies into deep space. In this gravitational ballet, a planet can be ejected entirely, accelerated to escape velocity, and doomed to drift forever. The second theory suggests that some rogue planets form directly from collapsing clouds of gas, like failed stars, too small to ignite nuclear fusion, yet too large to be called asteroids. Massive rogue planets, some the size of Jupiter or even larger, blur the line between planet and brown dwarf. Despite their cold loneliness, rogue planets might not be entirely dead. Jupiter's moon, Europa, and Saturn's Enceladus have subsurface oceans kept warm by internal tidal heating, not sunlight. A rogue Earth-sized planet with a thick atmosphere or insulating ice shell might trap internal geothermal heat from radioactive decay. Under these conditions, liquid water could persist beneath the surface, forming habitats shielded from cosmic radiation and interstellar cold. In theory, life could exist in such underground oceans, feeding on chemical energy as it does around Earth's deep-sea hydrothermal vents. Some rogue planets might even carry moons. If a gas giant is expelled from its star system with one or more moons still bound to it, those moons could experience tidal heating, further enhancing their potential habitability. In this scenario, life could exist beneath icy crusts, illuminated not by sunlight, but by the faint auroras of a distant, lonely world, glowing dimly against the backdrop of the galaxy. Where rogue planets represent isolation, the TRAPPIST-1 system represents closeness, density, and the delicate balance of habitability. Located 39 light-years away in the constellation Aquarius, TRAPPIST-1 is a tiny ultra-cool red dwarf star, barely larger than Jupiter and only about 9% the mass of the Sun. Yet around this faint ember orbits one of the most extraordinary planetary systems ever discovered. 7 Earth-sized planets, all tightly packed within a space smaller than the orbit of Mercury. In 2017, using the TRAPPIST, Transiting Planets and Planetesimals Small Telescope, in Chile and the Spitzer Space Telescope, astronomers detected a chain of transits, planets crossing the face of the star and dimming its light by fractions of a percent. The system revealed itself like a cosmic puzzle box. 7 rocky planets, named TRAPPIST-1b through TRAPPIST-1h, each with sizes similar to Earth and densities suggesting rocky composition. Even more remarkable, at least 3 of these planets, TRAPPIST-1e, F and G, lie within the star's habitable zone, where temperatures might allow liquid water to exist on their surfaces. The planets are so close to their star that their orbital periods range from just 1.5 days to 18.8 days. If you stood on one TRAPPIST-1 planet's surface, neighboring worlds might appear larger than our moon in Earth's sky, glowing like planetary crescents. Their tight orbits form a resonant chain where each planet's orbital period is related to its neighbors through simple mathematical ratios. This resonance hints at a gentle formation process. Perhaps the planets were born farther out and migrated inward through the disk, locking into step as they did. Because TRAPPIST-1 is cool and dim, its habitable zone is much closer than the Sun's. Yet its planets are likely tidally locked, with one side permanently facing the star and the other in eternal night. On such worlds, the day side blazes with unending sunrise, while the night side freezes in darkness. But between them lies the Terminator region, a twilight ring where temperatures could be mild enough for oceans, rivers, and clouds. Some models suggest thick atmospheres or oceans could redistribute heat, allowing global habitability despite tidal lock. TRAPPIST-1 has become a prime target for atmospheric observation. The James Webb Space Telescope has already begun examining the starlight passing through these planets' atmospheres during transit. Early results for TRAPPIST-1b suggest either no atmosphere or one stripped away by stellar radiation. But the cooler planets, TRAPPIST-1e, F and G, may yet hold air and water. If oxygen, methane, carbon dioxide, or water vapor is detected there, it will mark the first step toward identifying life on Earth-sized exoplanets. There are challenges. Red dwarf stars are volatile in their youth, emitting flares and high-energy radiation that can strip atmospheres from close-in planets. Yet some planets might regenerate atmospheres through volcanism, outgassing, or protection from strong magnetic fields. Ice-covered worlds could shield oceans beneath their surfaces from radiation. Life, if it exists, might adapt to infrared light rather than visible light, harnessing energy from a star that glows more like a dying ember than a flame. Together, rogue planets and TRAPPIST-1 show the breadth of planetary existence. one class wandering, alone, in frozen darkness, the other crowded around a dim, flickering sun. One speaks to the resilience of worlds cast into cosmic exile. The other speaks to harmony, resonance, and the possibility of multiple habitable planets in a single system. Across the galaxy, worlds are many. Some roam freely, some cling tightly to faint stars, and somewhere among them, perhaps in darkness or twilight, life may open its eyes for the first time. Not under a familiar sun, but under alien skies. They erupt with a violence that defies imagination. Cosmic detonations so powerful, they can be seen across billions of light years, outshining entire galaxies for a brief, terrible moment. These are hypernovae, the most extreme form of stellar death known to science. A hypernova is not merely a large supernova. It is the collapse and explosion of a massive star so enormous, so energetic, that its core implosion tears open spacetime itself, often producing a long-duration gamma-ray burst, the brightest electromagnetic events in the universe. Where a typical supernova releases about 1,044 joules of energy, a hypernova can unleash 10 to 100 times more, a cosmic tantrum with the power to sterilize entire regions of space. To witness such an event, even from afar, is to glimpse the cosmos at its most furious. Hypernovae occur in stars that begin their lives far more massive than the Sun, perhaps 30, 50, or even 100 times solar mass. These titans burn hot and fast, living only a few million years before their cores collapse under their own weight. When the iron core reaches a critical mass, gravity wins, and the star implodes. In a normal core collapse supernova, this implosion rebounds, blasting the outer layers of the star into space. But in a hypernova, the collapse is so extreme that the star forms a black hole almost instantly. Surrounding material falls inward, forming an accretion disk that spins at relativistic speeds. Magnetic fields twist around the forming black hole, and jets of energy drill through the dying star's poles, emerging as beams of gamma radiation that can travel across the universe. These gamma-ray bursts, GRBs, are so intense that if one occurred within a few thousand light-years of Earth, it could strip our planet's ozone layer and extinguish life. Thankfully, hypernovae are rare, occurring perhaps once per million years in our galaxy, and their jets are highly directional. But in the early universe, when massive stars were more common, hypernovae lit up the cosmos like cosmic beacons. They played a crucial role in enriching space with heavy elements. The extreme conditions inside hypernovae may even forge rare isotopes and elements that cannot be produced in ordinary supernova. The first well-studied hypernova was associated with GRB 9AE0425 and SN 1998 BW, a galaxy 120 million light-years away. The explosion was unusually luminous, energetic, and fast-evolving. Since then, astrophysicists have identified many more hypernova candidates, often linked to long-duration gamma-ray bursts that last several seconds to minutes. Collapses, the collapse of massive, rapidly rotating stars directly into black holes, are the leading model for hypernova formation. These events are not merely explosions, they are cosmic births, forging black holes and spreading metals essential for planets and life. Where hypernovae represent the cataclysmic death of massive stars, soft gamma repeaters, SGRs, represent something very different. The restless fury of magnetars, the most magnetic objects in the universe. A magnetar is a type of neutron star, a city-sized ball of degenerate matter left behind after a supernova, with a magnetic field so intense that it defies comprehension. The Earth's magnetic field is about half a Gauss. A typical magnetar's field is 1014 to 1015 Gauss. That is a trillion times stronger than our planet's magnetism. If a magnetar were as close as the Moon, it could erase every credit card on Earth. If a magnetar sat half the distance to Mars, its magnetic field could distort the shape of atoms. Soft gamma repeaters are magnetars whose surfaces undergo frequent, violent starquakes. Their magnetic fields twist and strain the crust of the neutron star, an iron-nickel lattice a billion times stronger than steel, until it cracks. When this happens, the magnetic field realigns explosively, releasing bursts of X-rays and soft gamma rays. The energy liberated in one of these bursts can exceed the output of the Sun in a century. And yet, unlike GRBs, SGRs usually repeat, sometimes dozens of times, each outburst lasting milliseconds to seconds. They are the thunderclaps of an ultra-dense star's magnetic heart. The most dramatic event ever recorded from an SGR occurred on December 27, 2004. A magnetar, known as SGR 1806-20, produced a burst so powerful that it saturated detectors even though it was 50,000 light-years away, near the opposite side of the Milky Way. For a fraction of a second, it outshone every star in our galaxy combined. Had it been only a few thousand light-years distant, it might have disrupted Earth's atmosphere. This event revealed the fearsome power of magnetars and confirmed that SGRs are not minor bursts, but cosmic-scale magnetic eruptions. Magnetars are born from the collapse of massive stars, perhaps the very same kinds that produce hypernovae. But instead of collapsing all the way into black holes, some neutron stars are born rapidly spinning with intense magnetic fields amplified by a dynamo effect. Their rotational energy and magnetic stress keep them active for only tens of thousands of years, a brief lifetime in cosmic terms, before their magnetic fields weaken and they become quiet neutron stars. SGRs provide unique insights into the physics of matter at nuclear densities. A magnetar's crust is only a kilometer thick, but supports stresses equivalent to the weight of mountains on Earth. When it fractures, it vibrates like a ringing bell, sending seismic waves through the star and twisting magnetic field lines. These starquakes reveal information about the neutron star's interior, whether it contains exotic states of matter-like superfluids, hyperons, or quark condensates. Together, hypernovae and soft gamma repeaters form a narrative of cosmic violence that spans scales, from the collapse of giant stars that shake the universe with gamma-ray bursts to the splitting crusts of neutron stars strapped in their own magnetic prisons. One marks the creation of black holes, spreading heavy elements across the galaxy. The other marks the tantrums of those stars that stopped just short of becoming black holes, instead becoming magnetars of unimaginable power. Hypernovae reshape galaxies. Magnetars reshape spacetime around them. Hypernovae are catastrophic finales. SGRs are relentless echoes. In these extremes, the death of the most massive stars and the eruptive lives of neutron stars, we see the universe's raw power. Hypernovae forge the elements that build planets and life. Magnetars test the limits of physics and remind us that even small stars can unleash unthinkable force. Both phenomena speak to a cosmos that is not quiet but alive with energy, collapse, and rebirth. They are among the gentler explosions of the cosmos, yet still powerful enough to briefly turn a faint star into one of the brightest objects in the night sky. Classical novae are not the catastrophic endings of stars, but rather their fiery outbursts, cosmic tempests born from intimacy, instability, and the relentless pull of gravity. Unlike supernovae, which obliterate stars completely, a classical nova is more like a stellar exhalation, a sudden eruption on a white dwarf surface, triggered by a slow accumulation of stolen matter. And these eruptions, though brilliant, are only temporary states. The white dwarf survives. It can erupt again. It can repeat its fury for thousands or millions of years. Classical and recurrent novae reveal an exquisite cycle of destruction and renewal, one of the most elegant dances in astrophysics. A classical nova occurs in a binary star system where a white dwarf and a companion star orbit closely enough for the dwarf's gravity to siphon gas from its partner. The companion is often a main sequence star, but may also be a red giant or subgiant. Hydrogen from the donor star streams toward the white dwarf. It forms a swirling accretion disk unless the white dwarf's magnetic field is so strong that it channels gas directly onto its poles. In most systems, the disk funnels the hydrogen slowly downward until it settles onto the white dwarf's surface. Here, under immense gravity, the gas is compressed and heated. Eventually, the conditions at the base of this accumulating hydrogen layer become extreme enough to ignite runaway nuclear fusion. The white dwarf does not explode, only its surface does. Hydrogen fuses explosively into helium, producing a thermonuclear flash that ejects the outer layer of gas into space at speeds of thousands of kilometers per second. For a brief period, hours or days, the system brightens by up to 10 magnitudes, sometimes becoming visible to the naked eye. This sudden flare is the nova, a new star, nova stella, as ancient observers once believed. In truth, it is not a new star at all, but a long-existing white dwarf erupting after centuries of silence. Classical novae enrich the interstellar medium with fresh material. Their ejected shells contain hydrogen, helium, carbon, nitrogen, oxygen, neon, and other elements processed in the intense heat of the thermonuclear runaway. Over time, these shells expand into delicate nebulae, thin and spherical, fading into the darkness. Some novae are surrounded by faint, ghostly halos, the remnants of earlier outbursts long past. These shells reveal the story of the system's long life, each eruption marking a cycle of accretion, ignition, and ejection. The beauty of novae lies in their repeatability. Though classical novae erupt only once in recorded history, the system itself may undergo similar explosions thousands of times over its lifetime. The white dwarf remains intact because the amount of material it ejects is roughly equal to the amount it gained. Over cycles lasting tens of thousands of years, the white dwarf neither grows significantly nor approaches the Chandrasekhar limit, sparing it from the fate of a Type Ia supernova. But some novae test the limits of this balance. These are recurrent novae, systems in which eruptions occur on human timescales, decades instead of millennia. They are rare, with only about a dozen known in our galaxy, but they offer extraordinary insights into how white dwarfs accumulate mass and evolve. Recurrent novae host white dwarfs that are unusually massive, often close to the Chandrasekhar limit of 1.4 solar masses. Their high gravity means it takes far less accumulated hydrogen to trigger a thermonuclear runaway. As a result, these systems ignite frequently, every 10 to 100 years. RS Ophiuchi, one of the best-known recurrent novae, has erupted multiple times since the 19th century, including spectacularly in 2006 and 2021. It consists of a white dwarf and a red giant companion. When the nova erupts, the ejected material slams into the red giant's dense stellar wind, producing shock waves that emit bright X-rays. The system briefly becomes one of the most luminous objects in the sky at high energies. Another remarkable system is U Scorpii, a recurrent nova with eruptions occurring about every decade. Its sudden brightening is so dramatic that it has become one of the most anticipated astrophysical events, watched each cycle with precision by professional astronomers and dedicated amateurs alike. Each eruption provides a fresh opportunity to study the physics of accretion disks, nuclear burning, and mass loss. Recurrent novae are not just curiosities. They may be progenitors of type Ia supernovae. Because the white dwarfs in these systems are already near the mass limit, and because they may retain some of the accreted material after each eruption, they can slowly approach the threshold where carbon ignition in their core becomes inevitable. If the white dwarf gains more mass than it loses, the entire star may one day ignite in a runaway carbon detonation, destroying itself completely. In this sense, recurrent novae may represent the final steps in a long evolutionary path towards stellar death, slow accretors that eventually cross a point of no return. But not all recurrent novae are destined for obliteration. Some may stabilize, lose mass faster than they gain it, or eventually exhaust their companion star's material supply. The diversity of these systems, ranging from symbiotic binaries with red giants to compact systems with main sequence stars, reveals the complexity of binary evolution. Even small variations in the mass transfer rate, magnetic field strength, or orbital separation can drastically alter the frequency and intensity of eruptions. Classical and recurrent novae together illustrate a universe in which destruction and renewal are inseparable. Each nova is a cycle, a gathering of hydrogen, a sudden flash of nuclear fire, an expanding shell of enriched matter, and then silence as the white dwarf resumes its patient accretion. Over millions of years, a single system may undergo countless eruptions, each time contributing new atoms to the galaxy. Long after the outburst has faded from view, those atoms may drift into gas clouds where new stars and planets form. Every nova, then, is a contribution to future worlds. Each eruption of RS Ophiuchi or T Coroni Borealis, each ancient blast recorded in a faint halo around a distant star, is a reminder that the universe is not static. It recycles itself. It reshapes and replenishes the material from which later stars, planets, and life emerge. Even in explosive violence, the cosmos is building something new. And so novae shine not only as bursts of brilliance, but as markers of continuity, flickers of nuclear rebirth in binary systems where gravity binds two stars in a relationship both destructive and creative. They are small reminders of the grand truth that even the most violent processes in the universe can be part of its long, patient act of creation. It begins deep inside a dying star, in silence so absolute that even light cannot yet escape. the moment when the balance between nuclear fusion and gravity finally collapses. For millions of years, the star has fought against its own weight, fusing lighter elements into heavier ones to generate the pressure required to keep its structure intact. But once iron forms in the core, the star's defeat is inevitable. Iron cannot yield energy through fusion. Gravity tightens its grip. The core contracts, temperatures soar into the billions of degrees, photodisintegration tears apart atomic nuclei, electrons and protons cram together into neutrons, and the core snaps inward at a quarter of the speed of light. In this instant, the supernova has begun, but from the outside, the star still appears unchanged. The universe sees nothing. Not yet. Then comes the shock breakout, the brilliant birth cry of a star exploding. As the core collapses into a neutron star or black hole, an outward-moving shockwave forms, born from the sudden halting of the core's implosion and the immense pressure of neutrinos streaming outward. This shockwave travels through the interior of the star, ripping through its layers with unimaginable force. For minutes or hours, it propagates upward, heating and accelerating stellar material as it goes. The star's envelope begins to swell, its outer layers trembling under the pressure. Then, the shock reaches the surface. In less than a second, the trapped energy escapes in a violent flash, a sudden burst of light that can be brighter than the entire galaxy around it. This is the shock breakout, the moment the shock wave first becomes visible to the universe. It announces the supernova with a pulse of ultraviolet and X-ray radiation so intense that no telescope can fully capture it unless it is already watching the star at the right moment. The flash may last only minutes, sometimes even seconds. Most supernovae are discovered days after this moment, when their light has already begun to rise from the expanding debris. But the shock breakout is the true beginning, the instant when the star's death becomes visible. Shock breakout has been observed directly only a handful of times. In 2008, an amateur astronomer unwittingly captured a sequence of images of a galaxy where a red supergiant exploded as SN 2000D. When professional telescopes inspected the same region shortly afterward, the Swift X-ray telescope detected a massive burst of radiation. The signature of shock breakout, SN 2016 GKG, SNLS 04D2DC, and several others, have given partial glimpses of this elusive flash, but its speed and unpredictability make it one of the most difficult phenomena in astrophysics to observe. Even so, shock breakouts hold tremendous importance. They provide clues about the radius of the star, the structure of its outer layers, and the exact timing of the explosion. Observing them is like catching the first breath of a newborn supernova, where shock breakout marks the start of a supernova's visible life. Orphan afterglows mark the hidden remnants of far more extreme explosions, gamma-ray bursts whose deadly beams missed Earth entirely. A gamma-ray burst, GRB, typically shines only along narrow jets that erupt from a collapsing massive star or merging neutron stars. If one of these jets points toward us, we see a GRB, an intense flash of gamma rays followed by an afterglow of X-rays, optical light, and radio emission. But the universe is full of GRBs whose jets aim in other directions. For those events, the gamma rays never reach Earth. What we see instead, much later, is the faint, slowly brightening glow created as the jet slams into surrounding gas and decelerates. This is an Orphan afterglow, the ghostly footprint of a GRB seen off-axis. Unlike classical afterglows, Orphan afterglows lack the initial burst. The first light we detect is the late-time emission from the external shock as it expands and begins to radiate more isotropically. These afterglows are often seen in radio wavelengths, but can also appear in optical or infrared. They rise slowly, peak days or weeks after the actual explosion, and then fade over months. Because no gamma rays are observed, identifying them requires careful elimination of supernova, tidal disruption events, and variable galactic sources. Yet they hold extraordinary scientific value. Orphan afterglows are the missing pieces in the population puzzle of GRBs. For every GRB we detect, there are dozens, perhaps hundreds, whose beams never intersect Earth. If we can detect enough Orphan afterglows, we can estimate how many GRBs occur in the universe, how wide their jets are, and how much energy they release. This helps constrain models of hypernovae and neutron star mergers, including their contribution to heavy element formation, such as gold and platinum. Orphan afterglows also expand our ability to detect the electromagnetic counterparts of gravitational wave events. When LIGO and Virgo detect the merger of neutron stars, astronomers look for optical or radio afterglows. But if the jet is not pointed at us, the GRB gamma rays may be invisible. The afterglow, an Orphan, may be the only electromagnetic signature. One such example came from the famous neutron star merger GWDU 17017 in 2017. Although the gamma-ray emission detected was extremely weak and off-axis, the radio and X-ray emission that followed behaved like an Orphan afterglow, gradually brightening as the jet slowed. The event revealed a structured jet, extremely narrow and intense at its core, but surrounded by slower, dimmer layers. This layered structure may be common among GRBs, and solving its geometry requires more Orphan afterglows. Modern surveys, especially those conducted by facilities like the Vera C. Rubin Observatory and radio telescopes such as Meerkat and ASCAP, are expected to find many more of these events. They will appear as isolated brightening sources with no associated gamma-ray signal. Their rise and decay curves, combined with their spectral evolution, will allow astronomers to reconstruct the hidden explosions that produced them. In some cases, careful modeling can even determine if an Orphan afterglow came from a hypernova or a compact object merger. Shock breakout and Orphan afterglows represent two moments in explosive astrophysics: the first instant of light from a star's collapse and the lingering glow from a cosmic jet we never saw directly. One is the beginning, a flash announcing death. The other is the echo, a whisper revealing what happened unseen. Both phenomena underscore a profound truth about the universe. Much of its violence is invisible unless we learn how to listen for it. Together, they deepen our understanding of stellar death, jet physics, and the ways energy travels through space and time. And with each event we capture, whether a fleeting UV burst or a slow rising radio afterglow, we glimpse the cosmos not as a set of isolated explosions, but as an interconnected web of light, gravity, and hidden collisions, whose effects ripple far beyond their origins. They arrive from deep space at nearly the speed of light, charged particles accelerated by violent cosmic engines hurled across the galaxy by supernova shocks, pulsar winds, magnetar eruptions, or the jets of supermassive black holes. These cosmic rays, mostly protons and heavier nuclei, stream into the solar system invisibly, but when they strike Earth's atmosphere, they reveal their presence in spectacular fashion. A single high-energy cosmic ray colliding with a molecule of nitrogen or oxygen instantly creates a cascade of subatomic particles, a cosmic ray air shower spreading through the atmosphere like a branching lightning bolt made of matter instead of electricity. The first collision is unimaginably energetic. A particle, perhaps a proton, with the kinetic energy of a thrown baseball, slams into an atmospheric nucleus tens of thousands of times the energy achieved in human particle accelerators. In that violent moment, the original particle shatters, creating pions, muons, kaons, electrons, neutrinos, and gamma rays. These new particles, many of them unstable, travel outward in all directions, colliding with other molecules and generating yet more particles. The result is a complex, expanding flood of radiation traveling downward toward Earth's surface. By the time the shower reaches the ground, it may cover several square kilometers. The first hints of cosmic ray air showers came in the early 20th century, when researchers noticed that radiation detectors recorded mysterious signals that increased with altitude rather than decreased. Later experiments revealed that particle counts would spike unpredictably, suggesting fleeting but intense cascades sweeping through detectors. Today, vast observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, dedicated to studying these air showers. They use networks of detectors spread across huge distances, some filled with water to measure the Cherenkov light produced when particles move faster than light can travel in that medium. Others employ fluorescence telescopes that detect the faint glow of nitrogen molecules excited by passing particles. Cosmic ray air showers tell us about the most extreme events in the universe. The highest energy cosmic rays, called ultra-high energy cosmic rays, UHECRs, arrive with energies exceeding 20 electron volts, far beyond anything Earth can produce. Their origins remain uncertain. Some may come from the shock waves of hypernovae or the jets of active galactic nuclei. Others may originate from exotic processes like the decay of super-heavy dark matter particles or topological defects in spacetime left over from the early universe. Each air shower recorded on Earth is therefore a message written in subatomic particles, a hint pointing back to cosmic accelerators millions or billions of light-years away. When a cosmic ray triggers an air shower, most of the particles do not survive to ground level. Electrons and gamma rays produce a dense electromagnetic subshower high in the atmosphere. Muons, heavier cousins of the electron, travel much farther, sometimes reaching the ground or penetrating deep underground. Neutrinos, produced in abundance, pass through Earth as if it were transparent. The pattern of particles arriving at detectors reveals the energy, mass, and sometimes the direction of the original cosmic ray. By mapping these showers, scientists hope to pinpoint their astrophysical sources, solving one of astronomy's oldest mysteries. In the same universe where invisible particles create cascading avalanches in our atmosphere, another kind of instability unfolds around compact objects, events governed not by collisions but by gravity, magnetism, and rotation. Around black holes, neutron stars, and white dwarfs, matter spirals inward through accretion disks, structures where gas, dust, or stellar debris forms a thin, rotating disk heated by friction and magnetic turbulence. These disks are among the most luminous objects in the universe, glowing in X-rays, ultraviolet, and optical light. But accretion disks are rarely stable. They flicker, flare, collapse, and rebuild themselves according to the complex physics of angular momentum, magnetic fields, and radiation. Accretion disk instability is a broad category of phenomena unified by one principle. Disks that should be steady often are not. Instead, they experience sudden changes in brightness, abrupt surges in mass flow, or large-scale structural rearrangements. In black hole binaries, these instabilities power X-ray outbursts, dramatic spikes in brightness lasting days or weeks, driven by sudden increases in accretion flow. As matter piles up in the outer disk, cooling efficiently, it eventually becomes dense enough to heat to a critical temperature, ionizing hydrogen and triggering a thermal instability. The disk becomes hotter and more viscous, rapidly transporting matter inward. The system brightens dramatically. When the disk stabilizes and cools again, the outburst ends, and the system returns to quiescence. In young stellar objects, where stars are still forming, accretion disk instabilities drive sudden bursts of luminosity lasting years or decades. Fu Orionis-type stars brighten by factors of 100 or more as their young disks undergo dramatic structural changes, perhaps triggered by gravitational instabilities, clumping, or interactions with forming planets. These outbursts may play a crucial role in building the mass of newborn stars and shaping the architecture of emerging planetary systems. Around supermassive black holes in the centers of galaxies, accretion disk instabilities govern the flickering of active galactic nuclei, AGN. Variations in brightness, from slow changes over decades to rapid fluctuations over hours, reflect turbulence, magnetic reconnection, or density waves propagating through the disk. Some instabilities launch jets of relativistic plasma, linking accretion disks to some of the most powerful astrophysical phenomena, including blazars and radio galaxies. One of the most important sources of instability is the magnetorotational instability, MRI, a mechanism that allows magnetic fields to transfer angular momentum through the disk. Without MRI, accretion would be painfully slow. With it, matter spirals inward rapidly, releasing gravitational energy as heat and radiation. MRI can produce turbulence, waves, flickering, and periodic bursts. In some systems, changes in accretion rate can cause the inner disk to evaporate, forming a hot, geometrically thick flow known as an advection-dominated accretion flow, ADAF. In others, the disk cools and collapses inward, emitting striking outbursts. Accretion disks may also undergo radiation pressure instability, where the inner regions, so bright that radiation pressure overwhelms gas pressure, begin to oscillate between states, dumping mass inward and then starving the black hole. This may cause quasi-periodic eruptions or long-term luminosity cycles. The best example is the microquasar GRS 1915-105, which has displayed dozens of distinct variability patterns for decades, each driven by complex interplay between radiation pressure, accretion rate, and jet formation. Whether through the thin air of Earth's atmosphere or the dense, swirling disks around compact stars, the universe reveals itself in particle cascades and instability-driven flares. Cosmic ray air showers show us the universe's highest energy travelers, particles flung across unimaginable distances by ancient violence. Accretion disk instabilities show us the engines that power that violence. The disks that feed black holes, shape young stars, and fuel quasars. One phenomenon rains particles into our atmosphere. The other drives light into the darkness around collapsed stars. Together, they show the universe as restless, dynamic, and ever-changing, built on instabilities that shape galaxies, ignite bursts, and carry cosmic messages to worlds like ours. They occupy the strange middle ground between ordinary stellar outbursts and the catastrophic brilliance of supernova, cosmic eruptions that shine brighter than novae but fall short of the overwhelming intensity of a supernova. These are intermediate luminosity optical transients, or ILOTs, a broad and still mysterious family of explosive events that defy neat classification. They erupt suddenly, rising to luminosities 1,000 to 1,000,000 times that of the Sun, sometimes forming expanding nebulae, sometimes ejecting enormous amounts of mass. They last longer than novae, shorter than supernovae, and possess energies that fill the gap between the two extremes. In recent years, astronomers have come to view ILOTs not as rare anomalies, but as an essential category of stellar evolution, markers of violent, transitional phases in the lives of stars. ILOTs encompass a wide variety of physical mechanisms. Some arise from unstable mass transfer in binary systems, where one star dumps material onto another in sudden, overwhelming quantities. Others originate from eruptions of giant stars undergoing rapid evolutionary changes, their outer layers destabilized by internal forces. Still others appear to result from the merging of stars, intermediate stages between the gentle kiss of tidal interaction and the dramatic union that produces a luminous red nova. What unites them is their brightness, duration, and the complex interplay of mass loss, accretion, and stellar structure that drives them. One famous example is V838 Monocerotis, which erupted in 2002. Its light echoed off surrounding dust to form expanding rings, light echoes captured in breathtaking images by the Hubble Space Telescope. The outburst was not a supernova, nor was it a classical nova. Instead, it reached a peak luminosity somewhere in between, then slowly faded into a cool, red remnant. V838 Monocerotis expanded into a bloated supergiant during its eruption, hinting that the event may have been a stellar merger, a precursor to the category of luminous red novae. But its behavior was so unusual that it remains one of the defining cases of ILOTs, a reminder that the universe produces more than just simple, well-defined explosions. Eta Carinae, the great unstable star of the 19th century, is sometimes considered an extreme example of an ILOT. In the 1840s, it erupted in the Great Eruption, becoming the second brightest star in the sky. It expelled several solar masses of material, forming the spectacular homunculus nebula, lobe-shaped clouds expanding from the star at hundreds of kilometers per second. Today, Eta Carinae is understood as a massive, unstable binary system whose eruptions may be driven by complex interactions between its two stars, including violent accretion episodes, radiative instabilities, and possibly partial ejecta events resembling scaled-up ILOTs. Many ILOTs arise from red giants or asymptotic giant branch stars shedding mass violently before transitioning into planetary nebulae or becoming white dwarfs. Others are associated with failed supernovae, where the core collapses quietly into a black hole, but the outer layers undergo a partial eruption, a dim flash marking the star's silent disappearance. Because ILOTs involve so many pathways, they are often grouped into the QI, intermediate luminosity red transients, ILRTs, when they show cool, red spectra, or giant eruptions when they originate from very massive stars like luminous blue variables. But within the realm of ilots lies a more specific and increasingly recognized class of explosions, luminous red novae, the unmistakable fingerprints of stellar mergers. Luminous red novae are the cosmic equivalent of slow-motion collisions, two stars spiraling inward until their outer layers touch, mix, and finally merge into a single, larger object. Unlike classical novae, which involve surface explosions on white dwarfs, luminous red novae arise from the full-bodied union of stars. Their light curves resemble a hybrid of nova and supernova, a rapid rise to brightness, followed by a slower decline, accompanied by dramatic reddening as the ejecta cool. They shine more brightly than novae, sometimes nearly reaching the luminosity of faint supernovae. Yet they originate from entirely different physics, gravitational merging, not thermonuclear detonation. The story begins when binary stars lose angular momentum. Tidal forces, mass transfer, or interactions with circumbinary disks may cause their orbits to shrink over millions of years. Eventually, the stars come so close that one star overflows its Roche lobe, spilling gas onto its partner. The system becomes unstable. The shared envelope engulfs both stars. Friction inside the envelope causes the stars to spiral closer, expelling gas and dust in brilliant bursts. When the cores finally fuse into one, a luminous red nova erupts, the visible shudder of a new star being born. A dramatic example is V1409 Scorpii, discovered in 2008. Archival data from the Ogle survey revealed that its progenitor was a contact binary system, two stars sharing a common envelope that grew closer in orbit over time. Then, in 2008, the stars merged, producing a luminous red nova. This was the first direct confirmation that these events are indeed stellar mergers. Another example, M31RV, flared brightly in the Andromeda Galaxy in 1988. More recently, in 2015, the event known as M101OT brightened dramatically, likely marking the merger of two massive stars. Luminous red novae develop characteristic spectra dominated by molecules like titanium oxide and carbon monoxide, which form as the ejected material cools. Their color evolves rapidly from bright white to deep red. Dust forms in the cooling ejecta, often obscuring the remnant star for years. Infrared observations reveal the lingering heat of the newly formed star and the expanding dust shells around it. These events are important laboratory for studying stellar evolution, binary interactions, and mass loss. They reveal how common stellar mergers may be, perhaps far more common than once thought. The implications are profound. Stellar mergers can form blue stragglers in star clusters, stars that appear younger and hotter than others around them. They may form massive stars late in a cluster's life or produce rapidly rotating stars primed for dramatic magnetic activity. Some theories even suggest that stellar mergers could create the conditions needed for magnetic dynamo fields strong enough to form magnetars. Ilots and luminous red novae are therefore part of a continuum, a spectrum of stellar outbursts driven by interactions between stars. They represent transformation rather than destruction, stars shedding mass, stars merging, stars evolving. In these eruptions, the universe displays not only its capacity for violence, but also its ability to reshape itself. A nova leaves a white dwarf intact, A supernova creates a neutron star. But these intermediate transients create something entirely different, a new star forged from two. In the violent ballet of binary evolution, these explosions are the crescendos, moments of dramatic change, brilliant and short-lived, leading to outcomes that shape stellar populations for billions of years. They remind us that stars are not solitary actors, but often partners, locked in gravitational embrace, sculpting each other's fates. And each islet, each luminous red nova, is a page in the story of how stars live, evolve, merge, and begin again. They are explosions wrapped in violence upon violence, supernovae whose brilliance is not powered solely by the collapse of a star's core, but by what the expanding ejecta collide with in the dying star's immediate environment. These are shock-powered transients, the spectacular interaction-driven supernovae, where the blast wave doesn't simply expand into empty space, but slams into dense shells of gas previously expelled by the star. In such moments, the shockwave that tears through the stellar interior is only the beginning. Once it reaches the circumstellar medium, material ejected years or centuries earlier, the supernova ignites a new source of light, the violent conversion of kinetic energy into radiation. This interaction transforms the supernova into something far brighter, stranger, and longer-lasting than ordinary explosions. These events are typically classified as type II or Ibn supernova, with the N indicating narrow spectral lines generated by slow-moving gas in the circumstellar environment. That gas may have been lost in violent eruptions, such as those from luminous blue variables, or through intense winds from massive stars nearing the ends of their lives. When the supernova ejecta, traveling at thousands of kilometers per second, crash into this slower, denser material, the collisions generate powerful shocks that heat the gas to temperatures of tens of millions of degrees. In this cosmic battlefield, photons are trapped, ricocheting through the dense material until they escape as intense light. The result is a supernova that glows for months or even years, far outshining typical core collapse explosions. Spectra reveal complex profiles, narrow emission lines from slowly moving gas, combined with broader components from the fast-moving ejecta. Interaction supernovae can be so luminous that they were once confused with superluminous supernovae until the mechanism became clear. Their light curves often show erratic behavior, rising or flickering as different layers of circumstellar material are engulfed by the expanding blast. One of the most famous examples is SN 2006 GUI, one of the brightest supernovae ever recorded. It was initially suspected to be a pair instability supernova, but later evidence suggested that its extraordinary luminosity was powered by ejecta colliding with massive shells of material thrown off by the progenitor star before the explosion. The progenitor may have been an extremely massive, unstable star undergoing repeated giant eruptions. This type of pre-supernova mass loss creates a layered circumstellar environment, like rings of a cosmic tree, each awaiting collision with the eventual shockwave. These shock-powered transients provide unique insights into the last decades or years of a star's life. Stars do not always fade quietly into collapse. Many undergo spasms of instability, shedding enormous amounts of mass in unpredictable outbursts. The progenitors of Type II supernovae, often extremely massive stars like luminous blue variables, appear to experience violent eruptions shortly before exploding. For astronomers, interaction supernova act as a fossil record of the dying star's final breaths. The structure of the circumstellar material, mapped by how the shock heats it over time, reveals how the star lost mass in its final stages. These violent interactions also accelerate particles to relativistic speeds, producing bright radio and X-ray emissions as the shock plows outward. If shock-powered transients expose the tempestuous ends of massive stars, K-rich transients reveal something stranger: explosions that seem oddly weak, oddly fast, oddly misplaced, and oddly rich in one element: calcium. First identified as a peculiar class a little more than a decade ago, K-rich transients occupy a peculiar space in the taxonomy of cosmic explosions. They are fainter and evolve faster than typical supernovae, often peaking just below the luminosity of standard Type Ia explosions, but brighter than classical novae. Their spectra reveals strong calcium emission lines shortly after peak brightness, far stronger than those seen in other supernova types. By the time they fade, nearly half of the visible light emitted may come from calcium alone. But the real mystery of K-rich transients lies in their locations. Many occur tens of thousands of light-years away from any visible galaxy, out in the dark outskirts of galaxy halos, or even fully isolated in intergalactic space. They erupt far from star-forming regions, far from stellar clusters, far from any environment where conventional massive stars are born. Their offset from host galaxies is often tens of kiloparsecs, making them, quite literally, cosmic loners. What kind of star explodes so far from home, producing so much calcium? The leading theory suggests that K-rich transients are the result of white dwarf mergers, specifically the detonation of a helium shell accumulated on a white dwarf, or the merger of a white dwarf with a helium star. Over long periods of time, gravitational interactions in galaxies can eject compact binaries into wide orbits or sling them entirely out of galactic disks. These binary systems wander the galaxy for hundreds of millions or billions of years before merging. When they finally collide or ignite, the explosion occurs wherever the binary happens to be at that moment, which often turns out to be far from any visible galactic structure. The detonation process in K-rich transients is thought to be rapid and incomplete, producing copious calcium but not the iron and nickel typical of Type Ia supernovae. Because only a small amount of mass, perhaps 0.2 to 0.5 solar masses, is involved, these events brighten and fade quickly. Their rapid evolution, strong calcium lines, and remote environments are all signatures of explosions that originate from compact, low-mass systems rather than massive stars. K-rich transients hold great importance in cosmic chemical evolution. Calcium is an essential element in the universe, forming the bones and teeth of living organisms, the minerals in rocks, and the spectral fingerprints used to measure stars' compositions. Yet the origins of calcium have long been difficult to pin down. Standard supernovae produce calcium, but not in the quantities needed to explain its cosmic abundance. K-rich transients may be a key missing piece. Their explosions produce unusually large amounts of calcium relative to their mass, and because they occur so frequently in galactic halos, their ejecta may disperse efficiently into intergalactic space. Some K-rich transients have been found near galaxy clusters, suggesting that wandering binary systems can travel enormous distances under gravitational influences. Others appear near globular clusters, hinting at dynamical interactions in dense stellar environments. Their diversity of locations reflects a common theme. These explosions are not tied to youth, but to long, slow evolution in compact stellar systems. Shock-powered transients and car-rich transients illustrate two very different sides of stellar death. Shock-powered events reveal the chaos of massive stars shedding their skins in violent fits before collapsing. K-rich transients reveal the quiet, wandering deaths of old, compact systems exploding far from home. One is bright and prolonged, shaped by the hidden shells, a star built around itself. The other is quick, spectral, and elemental, a flicker of calcium-rich fire in the deep outskirts of galaxies. Both types remind us that not all cosmic explosions fit into neat categories. The universe does not obey our desire for simplicity. It erupts in diverse, intricate, and surprising ways, each transient illuminating a different path through stellar evolution, each burst a clue in the long puzzle of how stars live, die, and enrich the cosmos. They begin not as stars, but as whispers in the darkness, dense knots of gas buried deep within cold molecular clouds. These clouds, stretching across dozens of light years, contain the raw material for new suns, hydrogen, helium, and traces of heavier elements forged in ancient supernovae. But only in certain pockets, where gravity overcomes turbulence, where cooling allows contraction, and where magnetic fields guide the collapse. Do these knots become something more? They become protostars, the earliest stages of stellar birth, invisible to optical light, yet radiant in the submillimeter and infrared. Among them, the youngest and most deeply embedded are known as Class 0 and Class 1 protostars, celestial embryos still swaddled in the thick cocoons of the clouds that made them. A Class 0 protostar is not yet a star in any traditional sense. It has no stable nuclear fusion in its core. Instead, it is a collapsing mass of gas, only a few tens of thousands of years old, drawing material inward while simultaneously ejecting some of that material outward in powerful jets. In this earliest phase, nearly all of the system's mass still resides in the surrounding envelope. The protostar itself, small, hot, and turbulent, remains buried deep within it, invisible even to the sharpest optical telescopes. Only instruments like ALMA or the James Webb Space Telescope can detect the faint, infrared glow and the deep millimeter-wave shadows that reveal where the forming star lies. During the Class 0 phase, infill dominates. Gas spirals inward, heating as it falls, generating a luminous infrared core. Conservation of angular momentum ensures that collapsing gas forms a small, rotating structure around the protostar, the earliest version of a protoplanetary disk. Simultaneously, violent bipolar jets erupt from the protostar's poles. These outflows are not incidental, they are essential. Magnetic fields threading the collapsing gas twist and accelerate material outward, allowing angular momentum to be shed so that the rest of the gas can fall inward. Without these jets, stars could not form. The births of young stars are therefore marked by both furious ingestion and dramatic expulsion. As the system evolves into the class phase, the protostar grows more defined. The envelope thins as material accretes onto the central object and onto the surrounding disk. The star's temperature rises. The luminosity stabilizes. The bipolar jets carve clearer pathways through the molecular cloud, creating the spectacular Herbig objects, glowing shock fronts where the jets slam into surrounding gas. These objects serve as neon signposts of stellar infancy, marking the locations of hidden protostars deep within their dusty nurseries. By the time a protostar reaches the transition between Class I and Class II, much of the envelope has dissipated or accreted, and the disk emerges as the dominant structure around the young star. This disk, rich in gas and dust, is the cradle of future planetary systems. But even before this transition is complete, the protoplanetary disk is already shaping itself, flattening, cooling, fragmenting, and forming the essential architecture from which planets arise. A protoplanetary disk begins as a simple, rotating sheet of gas and dust, but it quickly becomes far more intricate. Turbulence develops, temperature gradients form, regions near the protostar grow hot enough to vaporize it and drive chemical reactions, while outer regions remain cold and preserve interstellar ices. Dust grains collide and stick, forming pebbles. Pebbles gather into kilometer-size planetesimals through processes like streaming instability, an elegant mechanism where gas drag concentrates solids into dense clumps. Over time, planetesimals gravitationally attract each other, forming planetary embryos. The disk is not uniform. ALMA's images have revealed that many disks possess rings, gaps, spirals, shadows, and asymmetries, complex structures once thought impossible at such early stages. Some rings appear carved by forming planets, their gravity sweeping paths clear of dust. Others arise from frost lines, where temperatures drop low enough for water, carbon monoxide, or methane to freeze, altering the density and opacity of the disk. Spirals may be produced by massive planets, stellar companions, or even magnetic instabilities within the disk itself. In the innermost regions, within a few astronomical units of the protostar, temperatures reach hundreds or thousands of Kelvin. Here, rocky planets like Earth eventually form. Farther out, in colder zones where ices dominate, giant planets and ice giants take shape. Beyond them, in the frigid depths of tens to hundreds of astronomical units, the disk's outer edge transitions into the birthplace of comets and small icy bodies. Protoplanetary disks are transitory, lasting only a few million years. As the young star's radiation strengthens, it begins to photo-evaporate the disk, carving openings and driving gas away. Jets, winds, and magnetic activity also contribute to the dispersal. Eventually, the once massive disk thins until only leftover solids remain: asteroids, comets, dwarf planets, and planetary bodies. Gas giants must form quickly before the disk evaporates, or they will never form at all. Chemical evolution within protoplanetary disks is equally remarkable. WST has detected complex organic molecules, methanol, acetylene, formaldehyde, hydrogen cyanide within these disks. The ingredients of life appear to be present well before planets form. Water vapor often fills the inner disk, while ice mantles coat dust grains in the outer reaches. These ices, enriched with the byproducts of high-energy radiation and cosmic rays, become the seeds of future comets. When a forming planet drags these icy bodies inward, they deliver water and organics to young worlds, just as comets likely did for early Earth. But even as disks provide material for building planets, they also regulate the growth of the protostar itself. Accretion from the disk onto the protostar occurs in bursts, brief episodes where large amounts of gas fall inward, dramatically increasing the star's brightness. These episodic accretion events, observed in FU Orionis and X Lupi objects, reshape both star and disk. They can melt dust grains, alter chemical pathways, and change the architecture of forming planetary systems. Protostars and their disks do not evolve smoothly. They flicker, erupt, rotate, fragment, and collide. Their magnetic fields twist violently. Their jets pierce their surroundings with hypersonic precision. Every young star is a tempest contained within a shrinking envelope of gas. A storm of gravity, rotation, radiation, and chemistry. And every disk is a crucible, a thin membrane between chaos and order, where fragmentation gives way to structure, dust becomes rock, rock becomes world, and worlds become systems. Together, Class 0 Class I protostars and their protoplanetary disks define the earliest chapter of stellar and planetary evolution. They are the cosmic wombs from which stars ignite and planets emerge. Long before a star burns hydrogen, long before a planet cools into habitability, long before a comet shines in reflected light, there is the protostar, warm and buried, and the disk, thin and bright, sculpting the raw matter of existence. From these forming systems come every future solar system, every rocky planet, every moon and comet, every world where life might someday arise. In the quiet darkness of molecular clouds, amid dust, magnetism, and turbulence, the universe writes its most important stories, the stories of beginnings. They are the first true stars in the universe's long process of creation, not yet stable, not yet serene, but unmistakably alive, burning, pulsing, flickering with magnetic fury. Tauri stars represent the chaotic adolescence of stellar evolution, the moment when protostars shed the last remnants of their birth envelopes and emerge into view. They are young, only a few million years old, glowing with a warm, bloated radiance as they contract toward the main sequence. Circled by protoplanetary disks, pierced by stellar winds, and racked by intense magnetic storms, they are the restless teenagers of the cosmos. A Tauri star still carries the memory of its protostellar past. It retains a large radius and a low surface temperature compared to mature stars of similar mass. It is fully convective, churning internally from core to surface, dragging magnetic fields upward in twisting arcs. These magnetic fields snap, reconnect, and flare violently, producing bursts of X-rays and optical light far exceeding anything our Sun produces today. Entire star spots, enormous dark patches caused by magnetic suppression of convection, can cover significant fractions of the stellar surface, creating erratic brightness changes over days or weeks. The young star spins rapidly, often in just a few days, its magnetic field interacting with its disk in a complex dance of braking, acceleration, funneling, and turbulence. Tauri stars still possess the disks that will eventually form planetary systems. Gas spirals inward through the disk, guided by magnetic fields onto the stellar surface along narrow columns. Where these accretion streams strike the star, they produce hotspots, regions of intense, localized heating visible in ultraviolet and optical wavelengths. This magnetospheric accretion is one of the defining characteristics of Tauri stars, a process that never occurs once the star reaches adulthood. As disk material continues to fall inward, the star grows in mass, still months or years away from beginning steady hydrogen fusion. Yet in its heart, contraction and gravitational heating are already producing luminosity. Two types of Tauri stars exist. Classical Tauri stars, which show strong accretion signatures, and infrared excess from their disks, and weak-lined T Tauri stars, which have shed most of their disks and show little evidence of ongoing accretion. Classical T Tauris can be dramatic, undergoing sudden brightening events when accretion surges or when their disks reorganize. Weak-lined T Tauris, meanwhile, are more stable but still magnetically active, emitting strong X-rays from their turbulent outer layers. These stars shine with spectral fingerprints rich in lithium, a key indicator of youth. Lithium is burned rapidly in stellar interiors once temperatures rise sufficiently, but T Tauri stars are not yet hot enough to destroy it. Their lithium abundance is therefore an age marker, allowing astronomers to identify young stars even when their disks have vanished. T Tauri winds carve cavities in the surrounding cloud, shaping the very environment from which they emerged. These winds, driven by magnetic pressure and intense radiation, can halt accretion and blow away any lingering envelope material. They also interact with the star's jets, producing complex outflows and Herbig-Haro objects that illuminate the regions around star-forming clusters. If T Tauri stars represent the youthful emergence of sun-like stars, then Herbig-A stars represent the luminous, hotter, intermediate mass version of the same evolutionary stage. These stars, between 2 and 8 solar masses, shine far more brilliantly than T Tauris. Their surfaces are hotter, their colors whiter or even blue-white, and their luminosity can exceed the sun's bifactors of hundreds. Like T Tauri stars, Herbig-A stars are young, still contracting, still surrounded by disks, still sculpting their environments through radiation and winds. But they live on a different scale, one defined by a higher mass, stronger ultraviolet output, and accelerated evolution. A Herbig-A star emerges from its molecular cloud earlier than a T Tauri star would, simply because its powerful radiation burns away its cocoon more quickly. But while the protostellar envelope may dissipate early, the circumstellar disk often remains, glowing in infrared as it absorbs and re-emits the star's intense radiation. Many of these disks display complex structures, gaps, rings, spirals, warps, hints of forming planets or companions. The visibility of these features is enhanced by the star's brightness, making Herbig-A stars prime laboratory for studying planet formation. While T Tauri stars are dominated by magnetospheric accretion, Herbig-A stars straddle a boundary where magnetic fields weaken with increasing mass. Herbig-A stars, at the low mass end of the class, sometimes still channel disk material along magnetic funnels, behaving like giant T Tauri stars. But Herbig-B stars, the higher mass end, are often too hot to support strong surface convection, and therefore lack the magnetic dynamo needed to create such funnels. Instead, their disks may accrete through boundary layer mechanisms, where the inner disk meets the stellar surface directly. This difference profoundly shapes their variability, emission lines, and infrared signatures. Herbig-A stars illuminate their disks with intense ultraviolet light, creating photodissociation regions where molecules are broken apart, atoms glow in forbidden lines, and chemistry evolves rapidly. Their disks also display polycyclic aromatic hydrocarbons that fluoresce under ultraviolet radiation, complex organic molecules that might populate early planetary environments. Observations with ALMA and JWST reveal that these disks often contain large dust grains, millimeter-sized particles that hint at the early stages of planet formation. Despite their higher masses and shorter lifetimes, Herbig-A stars appear capable of forming planetary systems, including giant planets orbiting far from the star. These young, intermediate-mass stars also drive winds, fast, hot, and sometimes collimated into jets. Their outflows carve cavities in their natal clouds, shaping the morphology of star-forming regions. Their radiation can trigger sequential star formation by compressing nearby gas, effectively igniting new generations of stars. In regions where massive Herbig B stars form, their feedback can even halt further star formation by stripping material away before it collapses. The evolution of Herbig A/B stars is rapid. They reach the main sequence far sooner than lower-mass stars. A Herbig B star may take only a few 100,000 years to ignite hydrogen fusion, while a Tauri star requires tens of millions of years. Yet in their brief pre-main sequence lives, they exert enormous influence on their environment. In both Tauri stars and Herbig A/B stars, we witness the earliest astrophysical chapters of stellar evolution. One class represents the youthful form of sun-like stars, turbulent and dusty, deeply magnetic, growing through episodic infall. The other represents the luminous adolescence of intermediate-mass stars, already bright, already shaping their surroundings with fierce radiation. Both share circumstellar disks where planets may form. Both display the chemical richness of infant star systems, and both illuminate the final processes that turn protostars into main sequence stars. Together, they form the bridge between darkness and starlight, between collapse and ignition. They represent the moment when stars step out of their cradles and begin for the first time to shine. They are the titans of the main sequence, the brightest, hottest, most massive hydrogen-burning stars the universe can produce. Type stars dominate their surroundings with overwhelming radiation, driving powerful winds, carve enginized bubbles into their birth clouds, and shaping the evolution of entire star-forming regions. Though they live fast and die young, their influence stretches far beyond their brief lifetimes. An O-type star need not burn long to leave a scar on the galaxy. Every moment of its existence is an act of cosmic aggression. An O-type star's surface blazes at temperatures exceeding 30,000 Kelvin, often reaching 40,000 or even 50,000 Kelvin. Its light is intensely blue-white, saturated with ultraviolet radiation capable of stripping electrons from surrounding gas and turning its local environment into a glowing H2 region. These stars are massive, typically between 15 and 100 solar masses or more, forming only in the densest and most turbulent pockets of molecular clouds. Gravity binds them together only with the greatest of difficulty, and even a small fluctuation in the collapsing cloud can send material streaming outward instead of inward. Their formation is uncertain, their survival improbable. Yet once they form, they dominate everything around them. The core of an O-type star is a furnace of hydrogen fusion proceeding via the CNO cycle, a catalytic chain driven by carbon, nitrogen, and oxygen. This process is highly temperature sensitive, meaning small increases in core temperature drastically increase the star's energy output. As a result, even a slight destabilization can send energy through the outer layers in sudden bursts that shape the star's wind. These winds, driven not by hot gas alone, but by radiation pressure, blow outward at thousands of kilometers per second. In some cases, the wind strips away the star's atmosphere, revealing deeper layers and accelerating the evolution toward the Wolf-Rayet stage. The energy released by an O-type star is staggering. A single such star can outshine tens of thousands of sun-like stars, and its radiation can sterilize regions of space hundreds of light-years across. In star-forming clusters like the trapezium in Orion, O-type stars sculpt proplyds, small protoplanetary disks, shearing them with ultraviolet photons and photoevaporative flows. Young planetary systems forming near these giants must fight to survive. Some disks dissipate rapidly, their future planets never forming. Others endure, shaped but not erased, creating worlds unlike anything in our solar neighborhood. Despite their enormous power, O-type stars are ephemeral. They burn through their hydrogen in only a few million years, racing through stellar adolescence in the blink of cosmic time. Their deaths are dramatic: core collapse, supernovae, or even hypernovae that seed the galaxy with heavy elements and carve expanding bubbles into the interstellar medium. Their remnants, neutron stars, black holes, or in the most extreme cases, magnetars, carry on their legacy in new forms of compact fury. Entire clusters are rearranged by the death of an O-type star. The shock waves ignite new rounds of star formation. Dust and gas clump, collapse, and begin again. In many ways, O-type stars are both destroyers and creators. If the O-type star represents the beginning of stellar extremes, high mass, high temperature, high luminosity, then the red giant branch, RGB star, represents a quieter but no less dramatic transformation. The end of hydrogen burning in low and intermediate mass stars. After spending billions of years on the main sequence, converting hydrogen to helium in their cores, these stars eventually run out of fuel in their centers. Gravity takes over. The core contracts, heats, and becomes electron degenerate, while hydrogen continues to burn in a shell surrounding it. The outer layers respond by expanding enormously, cooling as they stretch outward. A once stable sun-like star swells into a red giant, its radius increasing by factors of tens or even hundreds.